tomorrow, and the General Chair, Ralph Lemmel here, will be organising the panel, and that is a very topical topic for the very hot topic for the panel, linking it with recent developments in AI, and after the panel there'll be the awards for, first of all, the most influential paper from 10 years ago, which has been decided by the SLE Steering Committee, and there will be then the most distinguished research paper based on the reviews and scores from the Programme Committee, and finally a distinguished artifact which has been decided by the artifact evaluation chairs. So that will be after the panel in the last session, and we'll also be discussing the future of SLE in the closing moments there of the conference. And most important, we'll also on Monday evening have a possibility of having dinner together. And this is not exclusive just to SLE participants, but the idea is that it's primarily an SLE meeting, social meeting, and there's a QR code there for signing up for this meeting. We need the number, we need to give the number for the restaurant this evening after the last session today. We need to have that number to give to the restaurant to make a booking. And it's a 20-minute walk from the hotel. So Eric, would you like to say anything more about the restaurant?
Hi everyone. Yeah, it's just a 20-minute walk. It's sort of in old Pasadena. It's a nice walk. And if you don't get the link or the QR code, you can just track me down and email me. And I just need a rough number for the restaurant. They seem pretty relaxed about how many people. So if you miss, 17:30 and you're 2 minutes late, chill out. It's fine. Just let me know. I'll try and call them tonight with the number. But if you don't get it, just email me and we'll figure it out. But it should be pretty straightforward. So. Guests are welcome. Children are welcome. It's a brewery, so in the United States, dogs are welcome at breweries, it seems. So if you have your pets with you, great. But yeah, and it's a very wide open thing, so the more the merrier. So anything else? All right, thanks.
Thank you, Eric. And finally, I'll hand over to Ralph to say a little bit about the SLE next year.
Yeah, so we want to announce SLE 2025 already that early, because it's going to be early in the year, which you see from the submission deadlines there, which are in February, and the actual conference is in June. And I'm very much happy that it's going to be in Koblenz for the first time ever since we founded this conference. I was a co-founder in 2008. Has never been in Koblenz. Finally, it's coming also to my place, and it's going to be, of course, best SLE ever. It's a wine place, for what it matters. It has the Rhine and Mosel rivers. I'm not going to show you all kinds of photos here. You can indulge yourself on the internet. But it's going to be on the university campus, and we are going to have a nice social program. And it's not a standalone conference, so it's going to be co-located with what's called STUFF. Many of you might know STUFF, which is actually a multi-conference incorporating things like ECMFA, ICGT, and a whole bunch of other events. So, so we are not coupling up next year with SPLASH'. We're going to be in Europe, in Germany, in Koblenz. It's going to be relatively affordable, and SLE will be on 2 days of a otherwise 4 days conference program. If you have any questions, please get in touch. There's already researcher.org up and running. It's not yet the full set of events there. It's a little bit early, obviously, but SLE, The SLE call for papers already there, and please keep in mind these somewhat earlier, I mean significantly earlier, submission deadlines, so get ready and submit to SLE or also to any of the staff related events. Going to be a pleasure to welcome you also in Koblenz.
Thank you, Ralph. So that concludes the opening slides, so now I'd like to ask the invited speaker to come and connect his laptop, so we're ready for the keynote in a moment. So please just take a few moments to talk to your neighbors and relax, and then we'll get started with the keynote in a moment. Okay, let's carry on now and have the keynote. It's a great pleasure for me to introduce Professor Benoit Commal. He's Professor of Software Engineering at the University of Rennes and co-leader of the diverse research team there. As you may know, he's also editor-in-chief of the International Journal on Software and System Modeling and steering committee member for the SLE and Models conferences, among others. His research includes applications of software engineering to scientific computing, cyber-physical systems, and digital twins. This involves model-driven engineering as well as software language engineering, and he is very active in both the models and the languages communities. Benoit's SLE keynote today will address topics including software hyper-agility and adaptability. And the keynote has the intriguing title, which I hope will become clear by the end of the talk. There is only one time in software language engineering. Please join me in giving a warm welcome to the speaker.
Can you hear me?
No. Can you use this one?
I can. Can you hear me now? Yeah, excellent. Thank you very much, Peter, for the very kind introduction. Thank you very much to you, Juliana and Ralph, for inviting me this morning. I was super excited to be here and to give this talk this morning. Welcome everyone, welcome to this new edition of SLE, and thank you very much for joining this morning for this talk. When I have been invited, I decided to not really present you a very technical specific contribution, but rather to share with you the vision that we have my team, but also in collaboration with several colleagues over the world, and more specifically with one very close colleague that I'm working almost on a daily basis, who is Thijs van der Storm from CW, with who we are co-leading an associate team in between his group at CWI and my group at. And I'm super happy to see in this room many people that has been involved during their PhD, postdoc in the team. And I will, by the way, present some work that has been done by these different people. So if you have any question, maybe I can directly convey this question to the right people. And my objective by the end of this talk is really that there is only one time in software engineering, and so in software language engineering. So what I mean by this, when I'm referring to this notion of time, I'm referring to all the different kind of times that we can see in the different papers from the scientific literature. Each time we are providing new tools or new way of building tools, we try to characterize the base place where this tools is supposed to be used. And if you go through the literature, you can see many references to design time or development time, or even now training time, where we need to train our models before being included into the software systems, compile time, runtime, operation time, and so on and so on. And I had at some point some time to reflect on what do we mean by this time in software engineering. Is that really a step in the life cycle? That would mean that when we are in one time, we cannot be on the other times? Or is it more an activity, possibly an activity which is performed in parallel to other activities, meaning that we can be at the same moment in different times? Or is it just a tool? And for this, I try to make an exercise trying to build a very naive big picture of this different time in the context of software development. So in the context of software development, we are using a lot of different software systems. We are surrounded of software, both in our professional and personal life. So in a daily basis, we are relying on this as a end user. And as a end user, we are using these different systems in the so-called operation time. So operation time is when the software system is provided to the end user and can be directly used by the end user. And of course, this operation time is following a time where we build the software systems, right? Which is more referred as the development time. And during the last decade, we did a lot of work trying to make as smooth and automatic as possible the transition, the continuum in between the development and the operation times, trying to automate as much as possible with principal tools and methods provided in the context of DevOps for going from development to operation and back from operation to development, at the point that nowadays we have a very high release frequency of our different software systems. And now if I'm focusing on the development time, of course, for developing a software system, we usually need a lot of different stakeholders. And for trying to coordinate the different stakeholders and the different activities that they are performing during the development lifecycle, we put in place some methods. So here, for example, it's an illustration with a Scrum method, which is an agile method, but you can think to any kind of development methods that we are putting in place for mostly organizing ourselves as human in terms of activities that we need to perform for reaching a high quality software system at the end that can be deployed and delivered to the end user. But of course, all these different stakeholders are providing a lot of different artifacts. And we also need to coordinate not only the stakeholders, but the artifacts that they are building. And for doing this, we are using different tools and methods. The usual tools that we are using is a version control system, such as, for example, Git. But for using Git, we also need some methods for coordinating the way of using the tool. And for example, here I put an illustration of the Git flow, which is one way of managing the different branches and so on in Git in a given software project. Okay, so if we now focus on the different activities of these different methods and the different artifacts that are built, we can also see another dimension, which is more referred by design versus runtime. So what does that mean? So it can become more clearer if we take the example, for example, of the V lifecycle, where explicitly in the V lifecycle, the main objective was to have a left branch where we build the system, where we design the system, and eventually where we implement the system, and a right branch where we try to evaluate what we design on the left one by doing some static analysis, but most often some dynamic analysis, doing some debugging, profiling, testing activities. And for all of this, we need to run the system. So we need to evaluate by running, executing the system, which is already runtime. So it's a runtime which is during the development time, because we are still developing the system, but it's also a runtime that we use at operation time. I mean, if we know how to execute the system, it's a way of executing it while we are developing it, but it's also the way of executing it when we use it in some way. So runtime is already something that we can put in place both at development time and operation time. And it's also something that we can see in languages. When we build our languages, especially in the community of SLE, we build our languages having a syntactical domain, which is mostly used at design time for building our different programs or models with our domain-specific languages. But we also need to provide usually a runtime infrastructure, which can be in the form of a compiler that we use for evaluating, executing, running what we define in the context of the syntactical domain. And this runtime infrastructure can be used, again, at development time for doing some execution, for testing, for debugging, profiling, and so on, but also, of course, at operation time when we want to use the system. And last but not least, just to finish this very naive big picture, I also wanted to introduce another dimension, which is application versus domain engineering. Because, of course, when we engineer our software system, we engineer our a given application, but because we are developing and engineering very complex application, we need to rely some knowledge that we capitalized, and usually we are capitalizing this knowledge in a continuous way. And for this, we introduce another dimension, which is the domain engineering. So domain engineering is really when we capitalize this knowledge in very different forms. It can be, for example, through component, with component-based software engineering. So we capitalize our components that we reuse afterward for building a specific application. And we can reuse it for different applications. And as soon as we have many components, we need to deal in the complexity of these different components and to clearly specify when a configuration is relevant or not. And this the software product line community working on this with many tools and methods for doing variability management. And it is also what we are doing in SLE. When we employ some domain-specific languages, we are in some way breakdown our software development lifecycle in two parts. The one where we use the domain-specific language, which is at the application engineering level, but there is also, beforehand, the time where we developed our domain-specific language, where we capitalize the knowledge that we have in a given domain, and which is more at the domain engineering level, and which is usually, again, a very continuous process where we continuously capitalize our knowledge in that domain. So it's pretty naive and probably incomplete, but it was just an attempt to try to put together all these different dimensions. And then continuing thinking about this, what became clear to me is that we are organizing ourselves according to this different dimension. So for example, if I'm, and I've forgotten that now we are employing some AI models that we need to define and train beforehand we can use them, which is another way of seeing this difference in between domain and application engineering. So if we look at our community, basically we are more or less stick to this organization of the different dimension. And here are the different sub-communities of the software engineering community, where for all of these different sub-communities, we provided some principles, tools, methods that are really specific of the specific time that usually they try to target. And which is good. I mean, developing software is something very complex, and because it's very complex, we need, if we want to conquer, we need to divide. And it was very good to break down our own community in these different dimensions, different times, such as we can address the complexity of the development of software. And maybe the claim that I will try to explain afterward is that now we matured these different sub-communities, is probably a good time to unite all of them, such as we can have a more exhaustive way of engineering our systems. And if we look at the consequence of this, that if we see the traditional we are basically inheriting from this organization. we are inheriting of this organization is basically the Conway law applied to ourselves. We divided our software engineering community in a certain organization that we are inheriting for the organization of the development of our complex software systems. And it's not new. I retrieved this paper from Luciano Baresi and Carlo Ghezzi in 2010. And in 2010, there was already recognizing that the wealth of methods and tools that are used at development time to forge software have no more use when the software enters the runtime stage. And what I was explaining in this paper is that, so we basically try to develop a given system in a given domain. So domain in the large sense. It can be the application domain, but it can be also the environment in which the system will be used. And we try to develop this system in a given domain, such as we satisfy the given requirements. And what they was acknowledging in this paper is that we, at development time, we try to provide the best quality software system that meet the requirements with regard to a given D, but the D, including the environment in which the system will be used, is continuously evolving and changing, which means that we continuously need to engineer our system for continue to meet and satisfy the requirements. And at that time, there was emphasizing mostly on the facts of the mobility. So D was changing because of the mobility, but nowadays is going way beyond only the mobility. But it's, and I will come back to this a little bit later, it's changing because we have very complex socio interaction with our systems, because we are involving in environment where there is some wicked phenomena that we need to consider and which are very difficult to analytically take into account beforehand when we develop our systems. And in the meantime, what we can observe is that we are taming a kind of what I call software hyper-agility. So hyper-agility is not the agility of the methods, like agile method, but it's the agility of the software itself. So software is moldable. It's one of the terms that people are using in the Smalltalk community. It's super moldable, and because that's moldable, we use this ability of being hyper-agile. It's a kind of multidimensional space in which we are involving when we are developing because function points, and the number of function points is evolving over the time. There are constants to take into account, and probably new constants to include during the life cycle. Think, for example, to energy consumption. That was not a concern 10 years ago in most of the software project, and which is super important nowadays to include. So we need to take into account these new concerns over the time. Space, which is most of the time very big. I mean, we are building very customizable or variable systems, such as we can meet different usage of the same system. We have a release frequency. I already mentioned this, but the release frequency of our software systems is really increasing and increasing again, at the point that we are basically continuously delivering our software systems as soon as there is a new contribution in the development time. We are targeting more and more execution platform, and we used to have software systems that was working or not, and which is not anymore the case. I mean, all our software systems are evolving in a correctness envelope, and we need to be very clear on this correctness envelope. And in time, systems adapt, but not anymore to a very fixed space of variable requirements that we used to define beforehand in the D that I was mentioning just in the slide before, during the development time, and then no changing for the rest of the life. But now the D is really changing, and it's changing most of the time due to an emerging chain of changing requirements. And these requirements are changing because most of the time we are taking into account or driven by the incoming input data. So we have a domain in which our software systems, which is continuously evolving, and we need to take into account of this evolution. Which means that software engineering must embrace this new temporal adaptability, and this new temporal adaptability that we need to consider in the context of this multidimensional space where we have all these different dimensions that are continuously evolving over the time. So that's lead to what the software engineering of my initial claim. And what I will try to present you is that we have a key cornerstone role in the SLE community, because this continuous software engineering can be driven at the language level, or can be capitalized at the language level, as we are always doing in the SLE community, such as we can continuous language oriented software engineering. But let's start by continuous software engineering. So what I really mean by continuous software engineering is the fact that we are continuously engineering our software systems at the point that the time where we are engineering a software system which is not yet in production is nowadays just a corner case. I mean, the mainstream case is that we are engineering a system which is already in production. And of course, it's raising a lot of challenges for us. Because we need to break really the different silos that we created in our communities that I presented before. We need to cross-fertilize the contribution that has been done in all the different sub-communities of software engineering. And we need to be able to continuously reevaluate all the decisions that we are taking when we are developing our software systems. So it's raising a lot of challenges, but it's also providing a lot of opportunities for us. Because if we are engineering systems that are already in production, we can leverage on all the data that we can collect from the system in production. What I mean by this is that we can leverage all the telemetry data, or the usage data, or the runtime data that we can collect, such as we can be well aware of the environment in which the system is used, such as we can take into account activities when we are engineering our software systems. So it's raising a lot of challenges, but it's also giving us a lot of opportunities for trying to automate and better clarify the environment in which the system is eventually used. And in the context of the software engineering, I did some literature review, and there is a lot of work that has been done on the past years. So it's very recent. If we look, there is a lot of papers that try to leverage the runtime data for automating some debugging session, or for automating the generation of test cases. I mean, if you think about test cases, it's beforehand the definition of input data. Why we should invent this input data if we can collect them from the runtime data, which are definitely clarifying in which context the system is used. I mean, it's better to test our system according to the way that it is going to be used in production, right? So it's for monitoring, it's the case for profiling, it's the case for debugging, it's the case for testing. There is a lot of work that is currently done in trying to cross-fertilize these different dimensions. So what does that mean for software language engineering? I mean, SLE is about providing language and it's definitely the place here where we try to define the future of the experience of our developers, whoever are these developers. That can be software engineers, that can be domain experts, that can be scientists, that can even be citizen developers. For all of them, we need to shape the experience in the future that they will need for engineering in a continuous way the systems that they are building. And for this, I will, this was the main vision that I wanted to share with you. And now I will try to illustrate this vision with some work that we did in the past years and even months in that context, and just to present you how this vision is driving the different contributions that we are working in my team and in the context of the associate team with CWI. I will present you some work that has been done on self-adaptable languages, so to make sure that our software languages that we are building can continuously evolve, even dynamically and automatically. And then as soon as we have this self-adaptable infrastructure, we can think about how we can coordinate the different languages, such as we can reason over the multidimensional space and having some decision-making processes that take into account the global big picture instead of just taking some optimal decision in our local concern where we use one language for one specific concern of our software system. And eventually I will finish, if I have time, about the vision that we have in my group about the future of the ideas that we are providing on top of these software languages, that I will not call anymore only integrated development environment, but more integrated and continuous development environment. Okay, so let's start by the first part about self-adaptable languages. So this vision about self-adaptable languages is something that we presented at 3 years ago. And self-adaptable languages are basically languages that provide capabilities for abstracting the feedback loop, so the design and execution of the feedback loop, while performing some trade-off analysis. And if I jump a little bit into the details of this paper, we introduced two feedback loops. One which is a runtime feedback loop that leverage all the data that we can collect when we run our software system. So the program is going to be run, and in that context we can collect a lot of information in which context it's run. And from this we can basically dynamically adapt language, and more specifically the execution semantics of those language, such as we can cope with the evolution of the environment. And I will give you some more details about this one. And another one, which is about the design feedback loop, is a feedback loop that leverages all the data that we can collect at design time in the IDE regarding the use of the language. And I'm not going to give you any details of this. I can just point to you that, for example, Juan de Lara in Madrid is working. There is some very recent papers that has been published on this feedback loop, and where the idea is basically to look at the usage of the language, such as we can detect, for example, some recurrent pattern that are really demonstrating that we are missing some abstraction in our language. And from this recurrent pattern of the use of the language, we can automatically verify some new abstraction in our domain-specific languages, which make the development of the domain-specific language continuous according to the usage of the language. But I'm not going to detail anymore. I already wanted to present some work that feedback loop, which has been basically the PhD of Gwendal Juno that defended 1 month ago. And during his PhD, he proposed two main contributions. One which is ASOS, which is a meta language for specifying and adaptive operational semantics, which is then compiled in the form of an interpreter, which is embedded into a framework, which is called SEAL, that operates the runtime feedback loop. So let me give you some details about this. So ASOS is something that has been done in collaboration with our colleague in Amsterdam, initially in CWI. Now they are moving in some universities in Amsterdam, but especially with Thomas and Damien, who are just here. So if you have any question about this, I will probably convey all the questions to them. Basically a meta language which is based on modular structural operational semantics. So modular structural operational semantics has been introduced by Peter Mays in 2004, and we use this ability of modularly defining operational semantics for, in a modular way, defining the semantic rules, but also the different adaptation that we can apply at runtime for adapting the behavior or the interpretation on the way of interpreting the different constructs of a given language. Rules such as they can be applied before a given semantic rule, after a given semantic rule, or in replacement by specializing a specific semantic rule, and everything done according to a feedback loop where we leverage the environment in which the system is executed. And there is some formal definition of ASOS, such as we can support the analysis of some properties, such as semantic determinism, termination, and completeness, with some limitation regarding this, because there is some evolution at runtime. But everything, if you need some details, are directly on the paper that has been presented last year at SLE. Just to give you an example, this one example of the use of MSOS, with which you can define the semantic rules. And basically, semantic rules is attaching a rule to a pattern AST, and that we apply in terms of writing for involving the execution state of our system. And in addition to the semantic rule, we can define some adaptation rule that match a given condition. And when the condition is old, on a given pattern of the AST, of the abstract syntax tree, we can apply this adaptation rule either before, but also after, or in specializing the one that should be executed by default. So this is the meta model. So this is pretty simple in terms of meta model of ASOS. Basically, an adaptive operational semantics is composed of a set of semantic rules. This is only an SOS. And in addition to this, we added some adaptation modules that for applying an adaptation rule, which is a semantic rule expressed in a similar way than we do in MSOS, in addition to specify if it's before, after, or in replacement by specializing the semantic rules by default that should be applied. And then, when we have the adaptive compile this into an interpreter, which is taken into account by SEALs, which is a language framework that basically apply the feedback loop. So in SEAL, we have the MapK loop, so the monitoring, analysis, planning, and execution. And during the planning, we define an impact model that is used for analyzing what are the best adaptation rules to apply. When the set of adaptation rule has been selected according to a given context, then at the execution level, we can, when we match the different condition and the different pattern in our abstract syntax tree, we can apply the different rules that has been selected, either before, by replacement, or after the by default semantic rule. And in that context, we can change basically the way of interpreting our different language concepts according to environment and according to some trade-off that we capture into the impact model. So if you go into the paper, you will see that we apply it to several languages. I'm giving you here 3 of them. So I will start by Mini Java, which is a representative example of an imperative purpose language, where we can basically reify everything that has been done in the context of approximate computing directly in the feedback loop of the language. So we can, for example, apply some loop perforation algorithm that usually we do it at the program level. So we need to implement this approximate computing technique directly into our program. And here we can capitalize it into the runtime infrastructure of our language, such as according to a trade-off in between the accuracy that we need. So for example, in the signal processing domain, we can play on the accuracy of the computations that we are performing according to it will take, and we can automatically, according to a given environment, apply the right trade-off and the application of the different adaptation loop. So we did it also for a specialized version of HTML, which is an example of a more declarative language, where the idea was to implement some trade-off in between the quality of the web page, of the rendering, and the energy that we need for doing this rendering. And the energy is not directly coming from the pure rendering algorithm, but also from all the data that we are transferring in between the server and the client. And in that context, we can dynamically adapt, for example, the quality of the images, or even the images that we are downloading and rendering in our web page. Or we can also, so we can degrade the images, we can conditionally load more or less information into the web page. All of this for trying to save some transfer of data over the network and to save some energy. Of course, with a trade-off with regard to the quality of the page eventually. And we also did it for a more DSL, domain-specific language, RobLang, which is a domain-specific language for specifying some mission for robots. It's an imperative domain-specific language where the trade-off was more about the time versus the energy. So the time for completing the mission with regard to the energy that we need to use on the battery of the robot. And sometimes there is some trade-off for saving some energy, even if the mission is taking more time. So for example, we can reduce the speed automatically of the motors according to the trade-offs that we have chosen. Okay, so now I presented this. I wanted to present you some other work that we did on the context of that vision, and especially in this context, we made adaptable the languages, but we made adaptable the semantics of the constructs, of the abstraction that we initially defined into our languages. But of course, there is some question on the way of engineering our abstraction directly into the languages that we are building. And we started to discuss with some colleagues 1 year ago, with regular discussion during 1 year about this question about how to engineer our abstraction nowadays. And we recognized that there was a lot of literature, for example, on the usefulness of the abstraction. I think we are all convinced in this room on the usefulness of the abstraction. At least if you're attending SLE, I hope that you're convinced on the usefulness of abstraction. But we acknowledge the fact that there was very few literature about processes for engineering those abstractions. And we decided to reflect a little bit on this, and especially nowadays in the context where we are continuously engineering our software system. So we did this work with some very close colleague on the past year, and we wrote a kind of white paper that has been published on arXiv. So if you want to look at this paper, it's abstraction engineering that you can retrieve on one of the key findings or the key message in this paper is that we jump into the details of the anatomy of the abstraction. And one of the things that we need to recognize nowadays is that the abstractions that we are using are not only defined by humans beforehand, as we used to do in the past, but they can be also inferred by the machine. When you're including some machine learning models into your software systems, at some point they are inferring some new abstractions that you need to combine with the ones that are made initially by the human. And those abstractions that are inferred, that can be inferred statically, but most of the time they are inferred dynamically. And they are not only inferred dynamically, but continuously over the life cycle of the software. They are dynamically updated, or they are even dynamically created. And which is of course raising a lot of challenges for us, because now we not only have to deal with the abstractions that we are defining ourselves, but we need also to combine them with abstractions that are more inferred from machine learning models and AI component in general. Which means that we need to manage these abstractions that are dynamically discovered over the life cycle. And those abstractions are usually coming with a lot of uncertainty that we need also to take into account. And eventually, when we are able to manage this complexity and uncertainty coming from the abstractions that we are using, we need to compose them. And nowadays, we need to compose this different kind of abstraction. And it's very new for us. I mean, what does that mean? It's not super clear, basically. But this is actually what happened in the modern software systems that we are building. And another question beyond the composition of this different kind of abstraction is how we can reuse them. How we can reuse them in different contexts, which means how we can transfer the knowledge that we use for inferring those abstraction initially in new contexts for developing other kind of software systems. And this led to a big challenge that I wanted to share with you, which is something that we just started very few months ago, working on this, about the hybridization of the different kind of models that we are putting in place in our modern software system development, where we have models that use man-made abstraction and models where we use inferred abstraction. And this is pushing us to think about what is the unifying theory of both deductive reasoning, the way that we used to reason on our system. I first define my abstraction, and then I'm using this abstraction for reasoning on top of my system, with more inductive reasoning coming from data science, where the abstraction are inferred from the incoming data over the time. So I think it's one of the big challenges that we have in our community in the near future, where we can use in our languages this different kind of abstraction for doing some hybrid modeling. So hybrid modeling is really when we coordinate the use of these different kind of models. So how we can coordinate the use of models as we used to define in the model-driven engineering community, for example, and the models coming more from the machine learning and AI community. And we can even go beyond the hybrid modeling, but we can go to adaptive modeling, where we use one model for adapting the other kind of models. So how we can use, for example, machine learning models for trying to infer or to refine an analytical model, or vice versa, how we can use, for example, an analytical model for inferring or for tuning the hyperparameters of our machine learning models. So all such kind of scenarios are more and more prevalent in the software systems that we are developing. And right now, we don't have anything for dealing with this. I mean, we know pretty well how to do inductive reasoning or how to do deductive reasoning, but really the cross-fertilization in between the two is a big challenge. And it's a bit challenge because it's also introduced some variability spaces, in the sense that I mentioned the uncertainty, but beyond the uncertainty, it's also coming from all the variabilities that we can find in our environment in which the different software systems are involving, and we need to take into account this variability. And beyond the variability management that we used to do, we introduced this term of deep. We should recognize that we have variability occurring in all the concerns, but more importantly, there is interaction in between these different variability spaces, and those interdependencies in between the variability spaces have impact on our software and system properties. And most of the time, we are locally reasoning on a given variability space, such as we can locally try to optimize our decision. What is the best decision that I have to do in this variability space? But we all know that accumulating set of local optimization is not going to provide a global optimization of all the concerns that we are putting in place in the development of our software systems. So we really need to capture these different variability spaces, interaction in between them, and being able to reason over these different dimensions and different variability spaces. So this is a vision that we presented a few months ago in a new conference, by the way, which is called REP, about reproducibility, which has been introduced by SIGSOFT, ACM SIGSOFT, and where there is many work that try to reduce this deep variability by trying to reduce the variability spaces and fixing a lot of things. Okay, so that's probably one way to do it. But to be honest, I'm not super confident that, it's something which is imposed to us. This variability is imposed to us. So we can try to remove it, but at some point it's going to fail. It's probably better to embrace it and to make sure that we can deal with this deep variability, which means that how we can formally or explicitly capture the different variability spaces, relationship in between them, and then providing some way of reasoning into this different variability spaces and interaction, such as we can find some global optimization over them. And in terms of global optimization, we can think about fixing one point in this multidimensional space, such as if we capture this configuration among the multidimensional space, we can reproduce the way of developing our software system. But more importantly, we can replicate in the sense that we can try to change a little bit and to play this variability space as we or other alternatives, or we can try to optimize. So we can optimize the quality of our software system. We can also validate our software system, basically, for example, trying to have a better robustness of our software system, because we know that the environment is going to change, so we can play with this variability to know in which context is going to work and in which context is going to fail. And we can even provide more better resilience, because we know that we can change dynamically the configuration over the time, and it will still continuing to provide the quality that we are expecting according to the requirements. And of course, this leads to a better support of a feedback-driven software development, because if we are continuously engineering our software system, we need to take into account the feedback from all the data that we are collecting during operation time, such as we can continuously re-evaluate the different decisions that were taken during the development of our system and possibly change those decisions according to the change of the environment in which the system is behaving. And it is software development, but we also did it, so there is a paper where we introduce basically the fact that we need to capture the different variability spaces, but beyond capturing the different variability spaces, we should expose some impact model, such as we can have a global feedback loop that reason on top of this impact model for trying to find a global optimization. And this is true for software development, but it is also true for complex systems and more cyber-physical systems. So this is a paper that we presented at AIRE this year, which was a collaboration with Airbus, an aircraft, a European aircraft manufacturer, where we presented this and we tried to discuss with them the relevance or not of feedback-driven support and how they can put it in place in the context of their company. And definitely the key finding is that they definitely need to continuously reevaluate decisions that they are taking when they are engineering the aircraft. And this continuous decision-making process is something which is currently very hard for them to handle, and this is what we are currently working with them for, providing them some support for this. So everything that I presented up to now was really building blocks, and all these building blocks need to be introduced into a continuous development environment, which in some way require to de-siloing software engineering with software language engineering, meaning in another way, we don't want to think outside the box. We want to just remove the box. Think about design time. If design time is also deploy time, it's also runtime. I mean, something which is super well known in the Smalltalk community, for example. If the ID is the environment, but also the language and the application itself, everything is mixed together. I mean, it's more or less modeling, it's more or less testing, it's more or less debugging or monitoring or whatever. And all of this need to be used by stakeholders like domain experts or software engineer, programmer, modeler, end user, developer. So everything should be supported by the future development environment that we are producing in support of the domain-specific languages that we are developing. So for this, the first thing that we did is in the context of a collaboration with several companies, especially Safran, which is an aircraft engine manufacturer France, but also with a startup that we started, which is called Twin IT, and where we worked on an engineering forge, which is, let's see it as the next generation of the software forges that we are using nowadays in all the software projects, where we try to capture this design space across the different variability spaces and the interaction and interdependencies in between these different variability spaces, such as they can continuously, over the life cycle, re-evaluate the decisions that they have taken by trying to explore in this design space and to try to optimize the decisions that they are taking with regard to all the different concerns that are involved in the development process. And this is done in the context, it's 10-second publicity on my side, but this is done in the context of the startup Twin IT, where they really work on tools and methods for supporting this continuous software engineering or even cyber physical system engineering by producing the tools, but also the methods for using these different tools. So if you're interested about it in a more industrial context, you can contact me and I would be super happy to discuss with you. But the forge is only for coordinating the different artifacts and the different stakeholders, such as we can reason globally on our system. We also need to have the development environment itself. And for this, if we think today on what we expect from an environment that will continuously support the engineering of our software systems, is basically what we call the digital twin. A digital twin is supposed to be a digital representation of a physical twin. This physical twin can be a pure physical system, but most of the time it's not. It's most of the time a cyber physical system, where the part of the cyber and the physical part can be very variable. Sometimes there is a lot of physical part and a bit of cyber software, and sometimes it's a pure software system. So the physical twin in some way is absolutely not physical, but it's a pure software system. And here I'm just taking one figure from our colleague from Aachen, especially co-authored by Bernard, who is in the room, where they did a literature review and a mapping study of the different digital twins that are used and published in the literature. And what we can recognize from this, the digital twin are not only used during operation, but it's really a tool which is employed for seamlessly following the continuous engineering processes from design time to runtime. And of course, you can be more or less active or not on the physical twin according to the different phases, but it's really a tool that you use all along the engineering processes. And if we look at the art and soul of our digital twin, there is a lot of models. There is a lot of models that are playing very different roles. So, of course, there is some prescriptive models, which are the ones that we are building for prescribing the systems that we want to build. But because it's employed all along the engineering process, we can also leverage, we can collect from the system or the environment of the system, such as we can also build some prescriptive models and the context in which the software system or the system in general is used. And then we can use this descriptive model for supporting our work in the definition of the prescriptive model. So it can be done manually. So for example, using this through support like linters and so on for trying to support us in the decisions that we are making in the definition of the prescriptive model. But it can be also partially automated by the use of some predictive models, any kind of machine or symbolic statistical models or whatever that we use for supporting us and helping us in the definition of the prescriptive models. And I will finish with this. I'm asking you the question: what is the future of ID in that lens? In the sense that if we think about IDs as digital twin for software systems, I mean, how we can experience our software systems through the ID continuously all along the life cycle, right from the operation into the development. like, for example, having linters that are fueled with runtime data, such as when we take some decision, when we program our software system, we can leverage all this runtime data. How we can cross-fertilize, for example, monitoring, debugging, and testing. I already mentioned this. I mean, there is no reason to define from scratch like this what are the relevant data for driving our debugging session or our test cases. I mean, there is no sense to just invent this runtime data as soon as we can just collect them from runtime because our system is already in operation. So I really want to raise this challenge for our community in the future and to think what should be the future of the IDs that we are providing on top of the domain-specific languages that we are defining. This was my last message. So just to conclude very quickly my talk, I think, sorry, that I convinced you that time to tame and to our software systems and to cope with the software hyper-agility that I introduced, that we continuously need to explore and to reevaluate the different decisions that we did in the past with regard to a changing environment in which the system is evolving. And for this, I mean, because we need to address this new temporal adaptabilities that I introduced earlier. And for this, we need to go towards a continuous language-oriented, of course, software engineering. I just presented few things that we did with this vision. I mean, it was just some spot for demonstrating you the kind of work that we can do as soon as we have this vision in mind. But I really think that SLE is the right place for shaping the future of the experience of our developers. Whoever are these developers, it can be software engineers, domain experts, citizens, developers. We are here for shaping the future of how they experience this continuous engineering of the software systems. And I mean, SLE is really the hometown where we cross-fertilize these different communities. I mean, it has been built by the cross-fertilization of programming language, of generative programming, of model-driven engineering, of SPL, software product line, CBS, component-based software engineering, and ontology. And now I'm just asking, what about the adaptation loop? What about DevOps? I mean, how we can also leverage everything that they did in the context of the engineering of the languages that we are doing, such as we can have some more augmented language analysis tools like the recommenders, linters, and so on. We can also combine live and exploratory programming continuously, so we can explore many different alternatives in our ideas, and we can bring together monitoring, debugging, test, and all this kind of activities. Thank you very much for attending this talk, and of course I will be super happy to discuss you. I don't know if I have to answer some questions, but more to receive from you some feedback about this vision, what you think about it, and yeah, I will be super happy to exchange with you. Thank you very much.
So we only have one microphone, so you can raise your hand if you have a question, and I will bring the microphone to you. You'll answer, and then I will bring it back to our presenter. Oh, more efficient. So I guess if you have a question, you can come up. Or if you want me to bring it, I can bring it if that's preferred.
Thank you very much for your talk. So when I saw the languages that you had, where you could tweak the behavior of the program as things happen and so on, have you thought about how that would also change the testing frameworks that we use and the testing languages? Because it feels that instead of testing, giving these inputs, produce this output, you have to do more like property-based testing or like change your approach to testing altogether.
Thank you very much. We currently have a PhD student working in the context of scientific computing. And it was super interesting because the rationale at the beginning of this a PhD was that, okay, we need to test our scientific models that we are using, by the way, for taking some decision on our daily life. I mean, we had a lockdown that has been decided by many governments based on scientific computing and the use of, and if you look, for example, at the last GIEC report, there is very few scientific models that are tested, and we try to understand why. And basically, in scientific computing, a scientific models for running it is usually using high performance computing for hours, days, or even weeks. And if we think about our test cases, I mean, if you think about GUnit, for example, or whatever, it's basically defining tens or hundreds or even thousands of test cases that are all running individually the software systems. How you can run thousands of time scientific models that take weeks or days, even days, for being run once. I mean, that doesn't make sense. And in that context, there is a lot of cross-fertilization in between the execution itself and how we can fuel some debugging activities and some test cases by minimizing the test cases that we try to infer from the actual execution. So the only experience that we have currently is in this context, but I'm pretty sure that we need to do it in other contexts. I gave some references in my talk, and all of them are ad hoc approaches that we also need to verify at the language level. How we can produce automatically the bridges in between these different tools from the specification of our languages and the coordination of those languages. So I really see a great future on this. I mean, it's super exciting and so on.
Thank you. Thanks for the talk. That was very interesting and inspiring at the end that SLE is the right place for a lot of this. But I was curious about the adaptive SOS, and you sort of think like, the motivation is I don't want to rewrite this whole specification with an adaptation. I want to have something that gets applied, and then, so my question is, does that sort of generate a new version of the plain SOS specification that then is used? But I don't think you do that. You sort of see the original one and the adaptation, and you read those sort of in combination to know what's happening. But do you do adaptations on top of adaptations? Do you get enough adaptations that you kind of lose an understanding of what the resulting SOS specification is? And do you want to sort of reify that adapted version so I can read that? Can you like talk about that a bit?
Yeah, thank you very much, Eric. So it's exactly this. If we look at the software systems that we are building, because we are evolving in a changing environment, most of the software systems need to embed a kind of feedback loop. In some software systems, I mean, it's a primary concern of the software system, the feedback loop. So think about an autonomous car. I mean, concern when you develop an autonomous car is to have a proper feedback loop that, and in to continue to implement it by hand at the time that you're developing the software systems. But there is many other software systems where the adaptation loop is not the primary concern. And it's not the primary concern at the point that the developer most of the time don't really know how to implement this feedback loop. It's not well done. And in all this context, we thought that it was a good idea to reify it at the level of the language infrastructure, such as the developer don't have anymore to deal with this concern. I mean, it's just implementing his regular system, and the virtual machine is basically implementing the feedback loop and changing the way of interpreting the different language constructs according to this environment. How it's done, we leverage modular SOS, such as we can modularly define our semantic rules, but also the adaptation rule, and everything is compiled is in a framework which is called SEALed. So SEAL is in Java. So all the semantic and adaptation rules are compiled to Java. And the SEAL framework is operating the feedback loop, doing the monitoring, analysis. And it's changing every time. And it's deciding the right adaptation. Then it applies different adaptation. semantics as a set of writing rules from SOS classically. So there is a set of rules. Yeah. Okay. So there is a set of rules complemented with these adaptation rules. And now the question is, do we adapt the behavior at runtime? So which means applying these adaptation rules. So either in complement of the other ones, before or after, or just replacing the initial semantics. So that's the only thing that we are doing. And for this, we wanted to modularly define our structural operational semantics. And that's why we used modular SOS. And one of the benefits, for example, with modular SOS is that you don't have to deal with the complete execution state, but only the one which is relevant for the rules that you are currently defining. So that's the kind of thing that we leverage in ASOS from modular SOS. So basically, it's just a specific use of modular SOS. The only thing that we extended is this ability of defining adaptation rules that can be applied before, in a replacement, or after. That's the only thing that we did on top of MSOS. Everything else is just a regular use of MSOS, basically.
Can I just ask then, if you have before and after, this suggests distinct times. And your whole message was all times are the same. I'm just giving you a little grief. So.
Yeah, of course. Good comment. Is there any other question?
So if I may take the opportunity to have a question myself. First of all, thank you for the presentation. I was very happy to see this, but a lot of these things are far beyond my imagination even, let alone my work. And so some element of something I once did that's been of some use in this context. But if I think about practical experience with software packages and applications, one of the main irritations I've always found is the breaking changes that occur when new package versions arise, and the lack of immutable, reusable components in the software development world. Is this something you're embracing, that you have a breaking change and this has consequences and people have to patch things down the line? Or is it that you're aiming at some nirvana where you have these reusable components that stay the same and people can rely on them? There are two different strategies there, and I'm just wondering where you stand on this.
Yeah, so that's a very good question. I mean, I don't think that we can really decide which approach we want to choose, because there is one which is us in the sense that we need continuously to change our component, and of course that can imply some breaking changes on the software system itself. And that's exactly why it's super important to be able to experience our software system through the digital twin. The digital twin being the place where we can evaluate this breaking change, such as we can see what are the consequences to resolve these differences and eventually to deploy the change that we want on the software system. So this detachment in between the physical twin, which can be a software system, and the digital twin, where we can experience through this digital representation, is super important.
Yeah, thank you very much, Ben. I also very much enjoyed your keynote. You made one point that this kind of classic view on software development also involves the idea that many of the early methods, like design methods, are suddenly then not important later on. And you also had this nice idea about the IDE being basically one place where it all comes together. I was just wondering, and then you had many nice methods at hand, like the adaptive models and semantics. I was just wondering, have you thought about using knowledge graph terminology and semantic reasoning, semantic data? Because much of what you say also seems to strike on what usually people emphasize in the AI context, like explainable AI, right? But some of what you explain could be seen as explainable software development. I mean, more than explanation, but explanation is also very important, right? And there's also this coming together of deductive and inductive reasoning also seems to call a little bit more for, you know, semantic data, semantic reasoning, symbolic AI approach. What do you think about this?
I think it was a very wise comment, and I think you said almost everything. I don't have to add anything. It's really a challenge for the future, but I think you're really right. And for example, we just started a few months ago a project where we try to deal with this model hybridization challenge, where knowledge graph is really at the heart of the project. So it's exactly the kind of solution that we are trying to experience for doing this. So I have no more to say because it's really future challenges, and I don't have any solution right now to present you. But it's exactly this. I mean, it's really a very wise comment and probably well said and better said than what I did during the talk. Thank you very much, Ralph. But yeah.
So maybe that's a good point to conclude this session by thanking the keynote speaker for his wonderful presentation here. Please join me. And it's just about time for coffee.
I'm Anna. I showed up late. I think good idea.
Hello, everyone. Let's start the first research paper presentation of the day with Christopher, presenting the cooperative specification via composition control.
Thanks. Hello, everyone. My name is indeed Christopher, and I will be indeed presenting cooperative specification via composition control. So to unpack the title, let's begin with the cooperative specification bit. This work is motivated by the data exchange application. It concerns a class of distributed systems that are really characterized by crossing organizational boundaries. As a result, we're talking about sensitive data that is subject to a multitude of very complex requirements with very complex interactions. So our approach to this is maybe not surprising to you. It is that we formalize the system using some kind of specification language, and then we use these specifications to reason about what the system can do, what the system is doing, and for enforcement, for controlling what the system does. And now, in this context of this problem, the aim of the game is that however we represent the specifications, they must capture all the agents' requirements, all these different organizations. So what we mean by cooperative specification is that the specifications themselves are constructed by these cooperating agents. They're trying to build a specification that captures all of their requirements without each of them stepping on each other's toes. For the paper and for the presentation, I'm going to be constantly using this very simplistic running example, which is suggestive of the sort of use cases that we have in mind, where we have just 3 agents representing 3 facets of a very complicated inter-organizational system. We've got administrator Amy, who's concerned with, let's say, the physical running of the system and the infrastructure. We have bailiff Bob, who's concerned with regulating what the system is doing at a more abstract level, at like the normative system level. And then we have data consumer Dan, who is just a user of the system that's driving the behavior forward and trying to make it do particular things in particular situations. In the paper, we really examine a space of different languages. My goal here is not for you to be an expert in any of these languages. I'm just going to be using 1 or 2 as driving the examples. So I'm going to play fast and loose with the syntax and the semantics of these languages. I hope they are clear from context. If something is not clear, please ask. But they all boil down to modeling this example. So let's concentrate on a particular case where these 3 agents come together and they want to specify this system by building fragments of an EFLINT specification, where EFLINT is a particular normative specification language. So Amy goes first, and she defines some fragments that, let's say, lays down the domain of discourse concerning the processing of data. So she introduces some relations. She introduces some aliases for different kinds of entities. So a subject is an instance of an agent. And then a bunch of n-ary relations for building up this domain. So for every instance of processing, it is a relation between some agent and some data. That's how you can read this. And what EFLINT is good for, among other things, is that you can ask it to enumerate the normative violations. So on the right-hand side, I'll be enumerating the violations. Right now, everything's very abstract. The scenario has not been populated with particular instances, so nothing's going on, and there are no violations yet. Now Bob comes along and builds onto the existing specification, introducing new kinds of relations and introducing inference rules for inferring the presence of relation members from other elements or the absence of other elements. In this case, Bob comes along and says, let there be this notion of consent, which relates subjects to processing events. And then here is a normative concept. It is a duty, which is kind of like a relation as we've seen before, but importantly, duties can be violated in a particular state of the system. And this one, long story short, says something like, whenever you have consent, whenever there is processing, you need to get consent. And you're in violation if the processing is happening without the consent being given. So this type has been defined and the inference rule is defined, but because there is no processing yet, there are no violations. Finally, Amy comes along and introduces particular a particular agent. In this case, Amy introduces herself into the domain of discourse, and some X-ray data, which is within the scope of Amy. So here we're identifying data with pairs. Now Dan comes along and says, all right, very nice. I'm going to be processing Amy's X-rays, and I'm going to change the definition of the need for consent and trivialize it. There's no need for consent anymore. So the knowledge base is now not trivial. There are certain things that are happening. There is processing, there is data. There's no consent, and there's apparently no need for consent. As far as eFlint is concerned, everything is hunky-dory, and the system has done some work, and they have cooperated successfully. So this is fine, but this is maybe not precisely what we had in mind. Kind of intuitively, what we have here is that the translation into eFlint has lost something. We've lost some kind of requirement that we had in mind at this meta level of how the specification is meant to be changed, that has not made it into the translation into the spec. So when you run it, we have things drifting out of sync. eFlint tells us all is well, but we know it's not. Okay, so cooperative specification is the building of these things. How can we kind of internalize these meta-level requirements such that we get closer to what it is that we want? What we would like to be able to express is to capture what Bob has in mind. Now, maybe this is something that you inferred for yourself, but I will just tell you that we want Bob to restrict the usage of this relation. So now not only is Bob saying, I have defined this notion of the need for consent, but this definition can, from this point on, cannot be changed in this certain way, and that way is that you cannot add conditions that remove instances. And now when we reintroduce what Amy and Dan did before, now the specification is violating in a new way, and that is that Dan has violated this new kind of requirement. Dan has gone against the rules of not adding a condition on the need for consent. So we've kind of brought the semantics of the language in line with what it is that we expect. Very nice. So now let's abstract away from the example a little bit and talk about what it is that we're doing here. So we're not interested in doing this just for eFlint. We're not interested in doing it just in this particular way. Let's talk about what are like the bones of a specification language that is suitable for this use case. First of all, there needs to be some set of programs that you can write. We want to be able to compose programs so that these contributions can be clumped together to represent their cooperation. And we want programs to have some meaning that is somehow slightly decoupled from the syntax of the program. This is to give us some wiggle room with the domain of discourse versus like this meta level. Okay, and then the last part that we add is that we say, in addition to this domain level meaning where you extract a model from a program, which is what is not surprising, we introduce a secondary valuation of programs where we're just going with something as simple as possible for now. You just recognize whether or not a given program is valid. Now, valid is just another meaning, but we attributed special usage at this meta level, and we use it to mean that something has gone wrong with a cooperation if the program is invalid. Okay, so I showed this diagram before, but let's be a bit more precise using the syntax that I've introduced already. Now, composition is this little circle operator, and now cooperative specification is the development of a spec that has this shape, where it is the composition of these little fragments that are stapled on one after the other, and each of them is contributed by a different agent, not necessarily distinct agents. And then the success of the cooperation predicates that you must never observe invalidity for any substructure of this composite program. So at no point must my contribution ruin the validity of what we had already. So let's go back to the example we had a moment ago and consider how this fits into our worldview. So somehow we want to arrive at the situation that when Dan contributes this final fragment that violates the requirement we have in our head, we want that to really translate into invalidity. So this is the situation we have right now. Unfortunately, it is valid, not quite what we want. Where validity here, I mean that there are no violations in eFlint. So in the paper, we propose a number of different extensions for the syntax and the semantics of the language that really kind of minimally disturb the domain of discourse, but they change this validity. And here, let's examine just one of them, where it really closely models with what I hinted at earlier, where you do some really static constraint on what kind of changes you can make to the program. So here I say very straightforwardly that this type, this relation need consent, cannot be modified by the addition of new condition by statements. This is something that you can check just by reading the program statements from top to bottom. You don't have to reason about the model. And this really creates what it is that we wanted for this particular case. So in this case, we're using what we would call like a static control, because it is entirely decoupled from the model of the program. You can really reason about it without thinking too deeply about the instantiation of the atoms. You don't have to ask yourself about the members of these relations. There are some obvious benefits to sticking close to a static definition of validity. Two that come to mind is that you can explain why the invalidity has arisen by something that the programmer understands. It is something that translates very directly to a point in the code. You can say, Dan is at fault. This line that Dan contributed is at fault, and it clashes with that line that Bob contributed. Very explainable. And if we expect that computing models can get expensive because perhaps you have combinatorial explosion, searching of instances to relations, it's beneficial to decouple validity. You might want to do some kind of preliminary pass over your program to look for invalidity before you go through the trouble of doing the models. Nice. Does this always work? Is static enough? So let's play with our example a little. What if Dan contributes this? So by the rules we've established so far, this is valid, nothing wrong. What Dan says is that, okay, he's not going to disturb the need for consent anymore because that would indeed invalidate the program. Instead, Dan says here that anytime there is processing, implicitly he has consent. This is great, right? So every time processing happens, consent emerges out of the ether for Dan. So we understand that now Dan has introduced another workaround for this kind of meta specification that Bob has in mind, but how do we approach this, right? Because if we were to apply the same kind of fix that we did earlier, then we would have to prevent Dan from being able to change consent, which is not what we want, right? There are perfectly reasonable cases Dan might want to introduce consent. It could be that Dan gives consent for something, right? We really need to do something a bit more subtle here. Okay, so in this case, it's very easy to imagine how we might want to do some more dynamic notion of composition control, where you define this validity in terms of the model. So this is appropriate because what we observe in this case is that the problem is arising from an interaction between the meta level and the domain level. We're really thinking about particular instances of consent and who is inferring them. So it's not really possible to so neatly separate the meta level and the domain level anymore. So fine, let's propose a different extension to EFLINT, perhaps on top of the one that we had before, where we say that you decorate your relation and you say that some field has to reflect the contributor. So precisely what this means is that every time you apply an inference rule, it keeps track of which agent has contributed that inference rule. And this raises invalidity anytime the one who contributed the rule differs from the field of that element. So this really captures precisely what we wanted, that Amy is the only one capable of saying that Amy gives consent. So because Dan does it here, it now raises invalidity. The explanation is still quite nice. It says something along the lines of the contributor of this rule mismatches the field of the elements. But you now have to understand a little bit about the domain to puzzle through what this error message means. So we've seen now a couple cases of how we attack, we intercept problems that we, role-playing as Bob, foresee in this cooperative specification scenario. And we identify this kind of pattern that we expect to cover pretty much all the cases we're interested in. And we call it a control triple, where you have the composition of 3 programs. where the first two are contributed by some entity that has gone first, and the third is the one that this entity wants to intercept. Decides is not good because it violates some meta requirement they have in their head. And so how precisely you want to do this is that you can separate your part that you contribute first into P1 and P2, where P1 concerns the domain of discourse, so previously with the consent and the need for consent and all that jazz. And then part 2, it does nothing to the model on its own, but what it does do is it ruins the composition with P3. So in the example we saw a moment ago, the addition of this clause to the data type does nothing to the model. It doesn't change who gives consent. It just changes whether the program is invalid. Oh, okay, well, I had that very nicely on my slide. Okay, and we observe that this is not really a radical idea, this notion that we introduce, in this case, a static constraint on what kind of programs we allow ourselves to write, to protect ourselves, to harden our programs against accidental bugs or to protect abstractions is really not that weird. Here, this notion of like a private access modifier, I can't remember exactly what they're called, but in Java and in C++, it's really not strange to protect the access of your fields. And now, rather than the scope, this would be which contributor is modifying this type. And it translates quite neatly to this P1, P2, P3 control triple that we mentioned before. So P2 has the job of controlling what P3 is allowed to do. Okay, so we've now seen two composition control features, but we've stuck with one language, EFLINT. Let's just, for the sake of spreading out over the search space, consider a new combination, including a new language. Instead of EFLINT, let's consider Alloy. I don't know, perhaps you guys could just raise your hand or shake your head or something to tell me if you are familiar with Alloy? Yes, okay, so like some smattering of yeses. Okay, so it's at the outset, it's not radically different. You're ultimately representing your domain in terms of relations, and you represent these as records, whose fields are projection functions to other types. But the fundamental difference is that in EFLINT, where you have violations witnessed by some undesirable fact popping up, in Alloy there is no such thing. It takes very much the constraint programming worldview, and that has an interesting consequence on cooperative specification. So let's build an Alloy spec, and I'll demonstrate what goes wrong. Here we have Amy quite closely modeling what we had before, but now rather than the state being implicitly transformed with the triggering of new postulations, adding of new facts with Amy adding data, that kind of thing, we have to model this a bit more explicitly with these state structures. If I write this and I run this with the Alloy analyzer, it will search for examples of members of these relations such that all my constraints are satisfied, where constraints at this moment are just kind of the arity of my relations and how they project to one another. I don't have any relations between the elements. So I press play and Alloy will emit, okay, this particular instance, they're called, satisfies your requirements. If there are two states and you can step from one to the other like that, whatever. Okay, so Alloy is nice for reasoning about particular instances. It does the work of enumerating instead of you, the programmer. So now here's a pretty simple spec that is only complicated because it is contributed very incrementally by a bunch of different agents doing something close to what we saw before. We have Amy modeling this notion of state, something a bit more procedural, process-oriented. Bob comes along and says, okay, there is this notion of consent, and I want to introduce, here I'm modeling a slightly different rule, and that is that we want to be able to delete data. If I recall, the idea here was to model this notion for the GDPR that it should always be possible to delete data. Okay, and now Dan comes along and says, here's something really modest. It says, there is some processing. It's not a very radical claim to make. But if you put all these together, Alloy will inform you that there are no instances. You've defined an unsatisfiable specification, But unfortunately, it doesn't give you any inkling as to why, because there is nothing witnessing the problem, right? It's just an emergent property of all these constraints interacting in a particular way. Now, this sucks usually when you're writing Alloy, but it's especially terrible in this situation where we expect Amy to be relatively ignorant as to what Bob is doing and vice versa. So what do? First, I just want to clarify what is actually going on with this scenario, because I think it's quite unintuitive. So let me demonstrate to you that if you remove any of these different extensions, suddenly the thing becomes satisfiable. It really is just all of them at the same time. So if you remove Amy's requirement that there are some states, it all becomes trivial, and that's fine, right? No states, there's nothing to be overconstrained. If you remove the right to erasure, that's fine. You just don't have any deletion. If you remove Dan's requirement, that, what does it say? Dan says that if you have deleted something, you can't process it anymore, which is quite reasonable, right? Sorry, that's Bob. That makes sense. Bob is enforcing what it means to delete something, right? So if you remove that, then deletion and processing become orthogonal, no problem. You can process deleted things. And finally, if you remove Dan's thing about processing, that's fine. There's no processing. So this is terrible because there's nothing to explain what is causing this invalidity, so it's not very actionable. If we observe the scenario in reality, what are we supposed to do? This is kind of, in the worst case, not anything we can do about it, because this is what we're asking Alloy to do for us. However, if you are in a scenario where you are Amy in this case, and you foresee that this situation is going to come up, you can change the definition of Alloy by just tweaking it a little bit, not changing what it means for something to satisfy the spec, but creating a static relationship between the rules again. So here what Amy has done has said that only I and Bob understand what it means to do processing. I don't want Dan to touch processing because he's going to mess it up. Now, the same spec becomes invalid. It has the same instances as before. It has the same domain meaning. But now the reason it is invalid has changed. It now says what has gone wrong is that Dan touched processing when he shouldn't have. He's constraining it. Okay, so we see it has some utility in this case as well, but it behaves very differently. So just to give you some context, what is the relationship between the kind of examples that I've demonstrated for you today and the contents of the article? In the article, we're a bit more systematic about what are the languages we're dealing with and what exactly our extensions do and what this has to do with the domain of discourse, and how exactly we expect people to process the data to contribute to specification. So if you're interested in the nuts and bolts, please read the paper. Why are we doing this? No, not why are we doing this. What are we doing next? We want to explore particular points in this space that I've kind of laid out for you today. There are a multitude of different languages, and as you've seen, the same composition control feature, this notion of sealing, behaves very differently in eFlint than it does in Alloy, because the languages are a little bit different. They're subtly different. And it takes a little bit of effort to figure out which combinations are actually fruitful. So we want to spend some energy next looking into particular combinations. We have done so to some extent already. And based on this idea, we want to develop DSLs that really take this notion of composition control at the outset. So we've found that, as I've demonstrated with eFlint, because violations are witnessed by something, these kind of bottom-up logic programming languages work very well for this case. You can really put your finger on what is going wrong. And so we want to minimize the pain. We want to start with some data log variants to do the exploration of this static dynamic spectrum. Okay, and then the final thing we want to do, and why we're going through all this pain, is that we want to use this in combination with another work that we've done that has to do with multi-agent systems where the agents are acting in accordance to policies, where the policies are changing under their feet all the time. Now you can imagine that the contribution of fragments to the policies we can use to model mutability. And we want to introduce this notion of validity to control what kinds of changes can be made to the policy. And with this, we can still do some meaningful analysis about what these systems can do, even though the policies are changing and you don't know what's going on at any particular moment. So that's all I had for you today. Thank you for listening.
Thank you, Christopher. Let's start with the questions.
Yeah, thanks for the nice talk. I had two questions, I guess, or a request and a question. One, if you can say again the difference between dynamic and static. I don't think I quite understood that. And my question was then, where you had this restriction that you could seal something so that no one could change it later, right? So with consent, you say no more changes to consent. Can you be less restrictive in that and say, well, you can change it, but it still has to satisfy some property that's been specified by the person who designed the notion of consent, right? Maybe you could make consent harder to get, but you can't make it easier to get consent. So.
Yes, those are great questions. Thank you. The distinction between static and dynamic that we have in mind is just really how much validity is coupled to the model. So this is not really meaningful unless you're examining a particular language with a particular notion of model. But in the case of EFLINT, for example, the programs are like at the type level, and the models are at the element of relation model level. And a static notion of validity would really examine the assertions without populating the relations at all. You would be thinking of all consent, any consent, that kind of level. Okay, and then for your question about this static sealing, I snuck this by you while you weren't looking. The definition of seal that I used the second time is not exactly the same, because I have this teeny weeny little suffix to the rule that actually creates an exception where it's doing something closer to what I had with the other approach, where now sealing becomes a function of not only who is adding the rule, not only which thing you're adding, but also who is doing the adding. And with this, you can model exactly the example you gave, where you say that I, Bob, am introducing the notion of consent. Maybe I will change my mind later to change what it means to give consent, but you can't change the definition of consent. And we find that a lot of other things we can model this way. You can always introduce an agent which represents the power to change the definition of consent. You just need a kind of a starting point for this reasoning.
I see that now, right? I guess, but this is a little more about who can make changes and not what kind of changes they could make, right? So you may decide that consent is initially freely given, and you can layer on ways to make it harder to get consent.
Yeah.
And maybe you get too many layers and it becomes impossible. But
yeah.
you have this idea that, you know, violating consent is a bad thing. And so we may see ways we want to layer more reasons why someone doesn't get consent.
Right.
And that's more about sort of what it is as opposed to who does it. So
I think they really do come together. So if you just kind of think about it bottom up, imagine that I've just given you a language specification for some wacky variant of EFLINT. You could examine what I've defined, and you can see, oh, there are some meaningful relations coming out of this definition that apparently you can't go back once you've added a rule to consent unless you do this. And for example, it doesn't quite work with EFLINT, but if you do this in Datalog and you add this notion of sealing, you're changing the language semantics in a subtle way that you're ordering the rules for the first time. So you can kind of change the interpretation of a program for the purposes of the meta level, but not the domain level. So we found that really subtle differences in the definition can create radically different power dynamics between these agents. And with that, you can model all sorts of crazy stuff like delegation and sharing of control, things like that.
Thank you.
you for your presentation. You were showing that when you were removing individual facts, you would get valid instances. And I guess those valid instances that you're getting, they are not in any obvious way useful in combination to spot the underlying issue, correct? So my next question then would be, is there any more, is there other kinds of transformations at a per fact level that you could perform in order to explore some search space so that you would touch closer on a satisfiable specification?
So you're trying to kind of you're trying to discover the problem from the program. I think it's generally very hard, and this is the experience of people writing these kind of constraint programs. I don't think there is like a universally good solution, because the level at which you're inputting your requirements mismatches the level at which you're reasoning case by case. And so the only thing you can do is some form of pattern recognition, right? But the way you would go about this in practice, because it's the only tool you have at your disposal, is to flip on and off fragments and see what's going on. You can kind of discover their interactions indirectly this way, but it's a massive pain because their interactions are so complex. I don't have a good answer for you, because by the time you've boiled down your spec to this level, you've lost this static information.
Okay, let's thank Christopher again for the night's presentation.
Thanks.
Now we have Nathan presenting toward generating series-based graphical editors from annotated meta models. You can start.
Okay, thank you. Yeah, okay. So yes, so I'm Nathan Richardson. I've been working at the University of York. I've been working on a tool, Aconite, which is trying to move towards generating series-based graphical editors from an annotated meta model. So during this talk, we're going to go over a running example, which is the project scheduling language, which we're going to use throughout the presentation to show how the diagrams and representations are being generated. We're going to have a quick look at the graphical representation, specifically having a quick look about why we need to be able to specify them specifically. We'll go over a targeted graphical modeling framework in Eclipse's Sirius. And then we'll have a quick look over the proposed tool, which is Aconite, and that will include a demo of the tool working, and then we'll have a quick look at the future work. So the project scheduling language is primarily focused on a project which is made up of a bunch of tasks, each of which can contain any number of deliverables, containing all of the people as well within the project, and this has a bunch of efforts which relate the tasks to the people and the percentage of their effort that they're going to put into that task. And also we have the fact that different tasks can depend on each other. So when we're doing graphical representations, the generic way of applying it, for example, whenever we're using object diagrams, that's a generic representation. Whenever we want to represent the model, we have to contain all of the information as we are using an untargeted diagram. This means that if you want to be able to visualize any particular interaction between any two elements, all the information needs to be in there. And this is a very inefficient syntax, and this also happens with, for example, effort, which in here is acting as an object the same as any other, whereas it's much more acting within the semantics of the model as a labeled edge. So what do? We use domain-specific representations. These are targeted representations containing only the required elements. They're manually defined, and they can have multiple representations containing all of the different subsets, and we can also see that we can represent, through the manual specification, them in the more semantically obvious way. So how do we do that? So one of the ways that this can be done is through Eclipse Sirius. It's an open source project which provides a model-based approach for graphical modeling. Yeah, and this can all be contained with multiple diagrams all being within the same artifact. This is counter to a previously popular technology in Eclipse GMF, which only supported a single diagram from a set of artifacts. It also has an interpreted it generates its representations through an interpreted manner, which means that you're able to tweak the model and immediately see the changes in the model that you are working on in the background. And this is unlike GMF, which required you to recompile and regenerate before being able to view the next model. And this was quite slow. So here at the bottom, there's just a quick link, which is to the gallery to show some of the industry uses of Sirius, because it is quite a common tool. So at a high level, Sirius is made up of three main concepts. These are the container, edge, and node mapping. These are contained often within the layer and the diagram. We're going to ignore them mainly for most of this talk. These can be contained within each other, so a container can contain other containers and nodes. It also does style representations. This is done through property views. These property views essentially just give you a way of editing all of the different properties in a way that makes sense, which you can see over here. And also the structure carries between the Sirius model and the spatial containment of the diagram. So here, if anything is contained within the container mapping, when we get to the representation, you will see that node or container spatially contained within its containment, as you can see down here. So one of the components of Sirius is the semantic candidate expressions. These are required for any domain-specific logic. For example, whenever you're trying to compute the elements that are shown within the diagram. So on the right here, we have an example of this. We're trying to contain all of the tasks from a project to then be able to represent them. And this is using a reference from the model. These are always required, and the users need to have some understanding of the meta model because, as I just said, they are references. The domain class is also required, and all this does is filter the types to make sure that they are of the right type. And the understanding of the meta model can become more complex if we have multiple layers of referencing, as it requires the user to understand the structure of the meta model itself, not just look at each individual reference. So I'm just going to quickly go over some of the areas of Sirius that are targeted with Aconite. So one of those is the reuse. The reuse within Sirius has two options. You have reuse mapping, which just points that the container is going to contain another copy of this person node up here. We can also do it with import-specific nodes. These essentially are another class of nodes which overrides anything that is written within it, and otherwise it will defer to its essentially parent. Both of these require the original to exist. Another part of Sirius is the way it's persisted. This is done with an XMI. As you can see, it is quite complex, but obviously it's mainly designed for data transfer and not readability, although it is readable compared to, obviously, binary. This means that singular changes can sometimes be easy to see. Other changes produce much worse results, for example here. And this is actually a really simple change, and we'll go over that a bit more in the later slides. So the proposed solution is based on Eugenia. This was designed to reduce the effort of using GMF by generating from an annotated meta model. The strengths of this is it was a single artifact, which was a lot easier to maintain, and it provided useful defaults. This meant that if you're sticking within the bounds of normal diagram styling, you don't have to specify all of the different features if it is within the default. The limitations, which stemmed from GMF, was it only worked with one singular diagram at a time, and only representations of direct references. So as we can see, Aconite takes from it. You can see the correlation between the two styles. So it is very Eugenia-esque. However, because it is in Sirius, which allows multiple diagrams, it also allows multiple diagrams. And it provides useful defaults targeted at Sirius. And this includes expressions. And So some of the key features of Aconite is we are using the same descriptors as Sirius originally had. The styling is integrated, and this isn't required, but you can integrate the styling into a single element. We're using inverted containment for all of our containment, which, yeah. And the automated indirect SCEs are being generated in the background, and that is on page 7 of the paper, if you want to take a look. So I'm going to quickly go through a demo to show you how it works. Okay, all good? Yes. So at the moment we have this basic shape of the Aconite. So the node has a name, a container, and a color, and a label expression. The label expression is pointing here at our attribute down here. We also have an edge, and this is following a very similar structure. It has the name, the color, and the container. This is generated and has pre-generated this. But what we're able to do is we can make any changes. So let's change this over to blue. Let's make sure to spell it right. And here we can regenerate. And because of the interpreted nature of Sirius, it automatically transfers over as soon as we have regenerated our own design, which I did by right-clicking and clicking here. So then we're able to show we're able to add more diagrams on top of this. So these new ones are very much following the same style. Here we have one that's hitting all of our defaults. So for example, the color is, it wants a light yellow, and that is the default. And it automatically defaults that the label expression should be name. And that is happening in the background. So this one is quite simple. And then here we have another one which is pretty much the same. The edge is actually inferring itself what it should be pointing at based on the class type here. And that is automatically going to pick up on this node, and even though it's in a different one. So we can regenerate. And there we go. So we have the new diagram, which has been generated based on that specification. One of the important things about this one is the fact that this is the first time that we're going to get use of the automatically generated SCEs with a bit more complexity, which I will show here. So this has automatically generated the referencing to have the 2 levels of referencing rather than just the one, which it's gone through the process of selecting which one is the best one for that specific case. So we're now going to add in the third diagram, which was in our examples, but I didn't go over it too much. And essentially what we're doing is we're adding in a reference between the effort that is applied for a task. And for this one, we're very much reusing all of the nodes that we had previously. And this means this is done by adding in to this container just the other diagram for both of these, and nothing else. Nothing else is needed for these, and it will automatically duplicate it in the O design in the background. And then we have another type of edge, which here you have to actually specify the source and the target, unlike in all of our other edges, which it was automatically deciding the source and the target because of the reference-based edge. So we can show that. So yeah, so that's that diagram. And then finally, the final example is our other reuse. So now what we're going to do is we're going to take the project diagram and we're going to edit it so that each of the tasks within here is going to... Oh, yeah. Each of these tasks is going to contain its deliverables. This will then be able to show the user the indirect dependencies that are happening between the deliverables within the tasks. To do this, we actually now need a container rather than a node. So what we do is we pull out that descriptor into a new line. And what we're able to do is we're able to use the extend keyword, which essentially gets it to point at the previous node, and it will automatically copy over all of the properties and override any that are specified within this annotation. So here we have a new container, which is the project diagram, and then this one is the effort diagram. Down here we can see within the container for us is irrelevant of whether it's pointing up at a diagram or a container node, which means that we can just add in the new container for the deliverable, and this will automatically generate in the correct style. And it will now contain within it all of the things that are happening within the original style without having to copy it across, despite the fact that in the background there's quite a lot of different things happening. And also by having attached this by having this extend keyword, it means that we only have one place to ever change the styling, so that we can keep our styling consistent between all of our different nodes and containers. So one of the other benefits of doing this is that versioning becomes a lot more consistent, as we now have a dedicated textual syntax, and the descriptors we use whenever possible are the same or a similar keyword. For example, if we're ever making something a little bit more specific, we try and keep the name as close to the original name as possible. And that is the actual change that was happening in our really complex one, and that isn't even all of the change. So yeah, in the future, we plan to do some usability studies around the time taken to create new diagrams and edit our existing models. Also, further development, we're planning on adding more flexible mechanisms for cross-referencing annotated elements. We're going to add refactoring support specifically around renaming, because if you think back to how the names were working, they might change. The container's name might change, and we want to be able to factor that in and be able to refactor down to all of its yeah, I can't remember the word falling out of my head. On top of this, we plan to move to generating other notations. This might come in the form of Sirius, which supports other notations other than node edges. So this will include maybe tables or sequence diagrams, depending on what kind of thing we get asked for. And then let's not skip this slide. We also are looking into the possibility of generating plant UML from the same Aconite annotated meta models, so that this can be used from web-based editors. So that's everything. There's a link at the bottom. Any questions?
Thank you, Nathan, for the presentation. Questions?
Thank you very much for the very nice talk. It's a very useful work in the sense that defining the representation in Sirius is very painful. So having something for supporting this is very useful and welcome. I have actually two questions. The first one, a very quick one, is about your perspective. I was just wondering if there is no way of supporting more static analysis of what we define in terms of consistency. So, for example, checking that we have no recursive containment, so containing something which is already contained, and such kind of things, which is more or less feasible in Sirius directly, because we have a tree-based representation of the different representations. But now it's textual, so maybe it's more open to do some error when we do this. So do you plan to have some support for doing static analysis or not?
So at the moment, there is already some static analysis happening in the background. The way that I was doing it for the demonstration was I was just copying them through. But if I had been typing it, you would have seen some yellow text come up, and there is some static analysis automatically happening in the background to make sure that there's no loops, as you said, and it's also checking that a name is there and it's got a container, and then the edges are contained within a diagram at some point. And yeah, that's all happening in the background. So yeah, there is more that needs adding to it. It does deal with a lot of the problems that you could create, but not all of them at the moment.
Okay. And my second question is, so basically the power of such kind of tools like Sirius is about the ability of handling and managing a big gap in between the concrete syntax and the abstract syntax. And if we look at Sirius, basically what we can directly do with Sirius is very naive mapping in between the concrete and abstract syntax. And most of the time in real world use cases, we need to defer this to what they call services, external services, which are basically Java code that do whatever you want. And I was just wondering, in your tool, can you refer to such kind of external services or not? I didn't see any example, but maybe you can already refer to an external code for doing this mapping.
Yeah, so the tool, whenever it, there are specific property names that you can have which automatically fall back on the Sirius version, which means that I could put in SCE or semantic candidate expression, and that would automatically fall back down on Sirius. I haven't quite added in the ability to have an annotation that adds in the Java specification for the bottom of the Sirius O-design file, but all of the rest of the stuff is there for it to work. That just needs adding, and I don't think that if people, as you have, like said, "Oh, we really need this," it would get added reasonably quickly. It's just a small annotation. It's just where it goes is currently the design decision that hasn't been made. Thank you.
Yes, thank you for the nice talk. So it seems that you use XML to store the models, right?
Pardon?
You use... Hello? Okay. You use XML to store the models, is that correct? So would it be possible to utilize some of the query syntax from XML to define user transformations over these models?
So yeah, so that one of the possibilities, so back when it was Eugenia, there were polishing transformations. It's quite possible that we could add in a polishing transformation style thing to the tool, and that would be able to generate, like, edit the underlying model, essentially.
Thank you.
It's a very nice approach. I would like to know a bit more about the limitations of this approach.
So yeah, at the moment, yeah, it doesn't handle the Java expressions, which is one of the main limitations. The way it's currently handling tools is not fully fleshed out. There are a lot of tools, if I quickly open it up, that I can show you. There are a lot of tools that are actually being generated in the background. It wasn't part of this talk, but the way that the non-automatic tools work is currently very complicated, and that's why the future work is to add in more stuff about how you can reference specific annotations. And that's quite a large limitation at the moment, is the fact that the tools need a way of being specified, and that's going to take a little bit of working out, but it is part of the way there. It's just kind of pushing it through, and I needed to do the paper at the time, so yeah.
Okay, nice. Thank you. Now we have James presenting the work toward an in-context LLM-based approach for automating the definition of model views.
Thank you. Good morning, everyone. My name is James, and I will cover the paper towards an in-context LLM-based approach for automated definition of model views. I am a PhD student, and this paper was written by me with my supervisors Hugo Brunelier, Massimo Tisi, and Gerson Sunier. Here is a quick agenda of the presentation, so I will start presenting a bit of the context and the background of model views and EMF views. I will go to the problem through using an example that I got from the tutorial, the EMF views tutorial. Then I will go to show a bit of our proposal solution that is using LLMs, and I will finish with the contributions and potential future work. So let's start with the context and background on model views and EMF views. When we are working on very complex engineering systems, it's very often that we need to use different models that are written with different language, conforming to different meta models. Often the software engineer will use EML to represent the software. Some other stakeholder can use SysML to represent other parts of the systems. We can use BPMN to represent the business, and even some DSLs to represent other specific parts of the system that we are working on. The challenge arrives when we need to combine all these models together somehow. We are trying to create a single modeling artifact that can somehow represent the whole system, or at least part of the system, hiding some information from everyone, or highlighting some information. This is what we are calling here as a model view. One potential strategy to cope with this challenge is to create a viewpoint. So we create a viewpoint based on the meta models that work as a meta model to this model view. EMF views is a tool that was created with this idea in mind. It is a tool that is used to create model views over EMF compatible models. We have the tooling works in a way that is scalable because we don't copy all the elements of the models to the model view. We only have some proxies that point to the actual elements in the model. What is the problem that we are trying to work over here? To show the problem, I will use an example on books publication. That's an example that I got from the EMF views tutorial website. This is a very straightforward example, but it already showed to us some challenges that we can work on. So on the left of the slide, I have a very simple meta model that represent books. So I have books and chapters with some standard properties. And on the right of the slide, I have a meta model showing a publication, also with some standard properties like the title, the name of the author, the year of publication, and so on. When we are using EMF views, the tool comes with a special DSL that is created to help us to develop this viewpoint. The language is called Viewpoint Description Language, or VPDL. And in this slide, I have an example showing to you how we can combine books and publications in a model view. You can also access this example on the EMF views tutorial. How we create, as you can see, looking to the language, it's a SQL-like language, so it's pretty similar with a database view. And we can define the view name, we can define the features. It means the properties that we are selecting from the models that we want that appears in the view. We also have this join construct that enables us to actually combine two different concepts from each model. We need to define, based on the RI, the contribution meta models, and we also can define the rules that we will compute this association. So for each join that we defined, we need to have a correspondent rule on the where block that will calculate how we will combine these two meta classes. In this case, I have a combination between a publication and a book, and I'm matching the title. So when the title is the same, I know that they should be combined in the view. I was able to create this viewpoint because first I know VPDL, and I also know details about the underlying meta models. But what we are trying to achieve here with our proposal is what happens when we have a very diverse team that does not know necessarily everything about VPDL, or they don't know everything about the models. We are trying to create some kind of tool, some kind of approach that can help the engineers to reduce the workload of the engineers, and also provide some kind of automation. So at least a starter point, how we can start the work with some kind of automation. one idea is to use LLMs. LLMs, as you may know, are large language models, a special kind of neural network that is based on the transformer architecture, and it was designed to process textual data. It has its breakthrough 1 or 2 years ago, and it can be used on a lot of tasks like text production, translation, text generation, and also text reasoning. Okay, so when we are thinking, okay, we have this problem of how to combine models in a model view, we have the language, what's the most straightforward approach that we can go? Let's go to ChatGPT, ask them, here are the plant-ML versions of my meta models. I want to create a view that combines books and publications. Give me the VPDL code. This is the result I got on a specific chat session that I had. As you can see, it makes sense, but not VPDL code. It do not look like VPDL code. And why it happens? Because ChatGPT, actually the GPT model that's in the background of ChatGPT, does not know VPDL. It probably does not part of their training data. It contains some hallucinations, so what is very common when we are using LLMs. It's syntactically incorrect. It is not VPDL, neither any other language that, at least the language I know, or a language that we can use. And also in the pairs that, in the combination of the classes they are proposing is not exactly the classes that we are expecting. The numerical data is on the paper if you want to see. So our solution is to somehow try to use LLMs to solve this problem, solve problems partially generating the view description with the minimal input of, from the engineers. On this slide, I have a diagram with our approach. We are relying here on prompt engineering first, especially chain of thoughts and few shot prompting, that are two techniques that are getting some traction on the LLM community. We are counting also on the decomposition of the problem. As I showed to you, the VPDL contains 3 very well-defined blocks. So we can try to decompose the problem of create a VPDL code in 3 different problems. We are trying to do not use retrieval augmented generation, neither fine-tuning. What are the 2 other potential techniques to solve the same problem? And we are using the same LLM that is used on the ChatGPT, the GPT-4o. Let us go step by step on our problem. As I said before, we are trying here to solve this problem with the minimal input from the engineer. So the inputs that we are expecting on the first step is just to receive the e-core meta models and small, or not, or at least small enough, a small description of the view. So the user does not need to know necessarily anything about the VPDL. They just need to provide a textual description of what they want to see in the final view, that we are calling here a user view description. The first step that we have is a pre-LLM step. We just convert our e-core meta models to use the Plant2ML notation. We did this in this way because of based on our own experimentation and also in other papers that deal with this problem, we know that LLMs understand better Plant2ML notation in comparison with the e-core or XMI notation. And then we go to the next step, that's the first LLM step. So what we did here, we create these prompt templates. Prompt templates are very long textual instructions that will guide the LLM to solve a specific problem. So in our case, we create 3 prompt templates. One just to define what elements will be selected by the LLM. Another just to define what pairs of meta classes will be combined. And the last one to define the rules of associations, how combine these models. In this slide, I have an example, just the first lines of the join. The the join prompt template. And what we did here, we inject the information that comes from the user, the core the plant ML net models in this case, and the user view description inside this prompt, and then send to the LLM. We are able to ensure that the LLM will answer us with a textual output because it's an LLM, but we can ensure that it's a JSON response, and we can then analyze this response. What we create here, we create a new component, output parser, that will analyze this response, this JSON response that came from the LLM, and check if it will if it respects some constraints, like if the meta classes that they are proposing really exist on the meta model and things like that. So we can iterate for each prompt template that that we create. We can iterate sometimes to ensure that the response respect these constraints, and also we can iterate for each one of these 3 tasks that we define: one for select, one for join, one for the where. It's important to note that the engineer that are using our solution does not need to edit, to change these prompt templates. The only thing that they need to provide is the meta models and the description. So this is the VPDL code that we use as a reference. As you can see, that's slightly different from the previous one that I showed, because here I have 2 relations, but the idea is the same. We are still combining books and publications as I showed to you. This is the reference output, and this is the final output of our approach using LLMs in the way that I explained. We can see that the properties that the LLM propose are okay, they match exactly the properties that we are looking for. On the join block, we can see that we have the 2 relations. We have the LLM get 1 relation in the wrong order, but it's almost the same relation, the same relation that we are expecting. And on the where block, as you can see, we are not asking the LLM to generate OCL. Actually, in the EMF views, we use ECL, but we can generate ECL code or OCL-like code to navigate in the models and create the combinations. Instead, we are asking the LLM to generate natural language explanation of how to combine the meta classes, and the engineer will be responsible to translate it to ECL in this case. So just for a moment, let's concentrate on the select and the join. So for the join, we calculate here the precision and the recall of our approach. As I said before, we have one exact match of the relations and 1 match but in the wrong order that we consider here incorrect. And for the selected block, for the properties that we are asking the LLM to select, we have an exact match in comparison with our reference code. I also want to highlight that we have 100% syntactically correct code. This is a VPDL code, or almost. It's a draft of a VPDL code. Even if it does not compile, it will be fairly easy for an engineer to convert it to a final VPDL code. And for the where part, since we are not generating the expressions, we are analyzing it qualitatively. So we know that from a human evaluation, it's satisfactory enough. And to also use LLM to analyze our final response, we are using an approach that's called LLM as judge. It's a approach that also getting some traction on the LLM community. When we ask another LLM on how hard it is to go from this generated code to my reference code, and we have a scale here, a kind of a grade. So just checking the quantitative analysis of the join and the select, together with this example that I showed to you, we also select 3 other views from the literature, 3 other views created with VPDL code, and I want to highlight again that we always have syntactically correct code, even though we don't have the best results on the precision and recall on all examples. You can also check the numerical evaluation on the paper. So I can start to conclude what we have as contributions on this work. On the technical side, we are trying to provide an in-context approach. It means that the user does not need to give any, does not need to have any special knowledge to use our approach. The LLM don't need to be pre-trained on the VPDL code. We are not expecting that it to be fine-tuned. And also, we are not expecting to use retrieval augmented generation, because both fine-tuning and retrieval augmented generation can have can be expensive, and can also bring other problems to the scenario. And we are using here VPDL as an example, but we can see that the same approach has also potential applications to other modeling languages. On the LLM side, on the application of LLMs for engineering problems, we are showing the feasibility of the use of LLMs to draft model views. Again, in the example we are using VPDL, but we can think on any other language to create model views. And we show something that show something that it's already on the standard knowledge, that the decomposition of the problem helps LLMs to better reason on the problem. So small problems are solvable for the LLM, and we can combine the solutions of each step in a final solution. We implemented our approach with a prototype using open source tools, more specifically LangChain. It's an orchestration framework for LLMs, and PyCore to deal with the core details of the meta models. And we also use off-the-shelf LLMs. For this experiment that I showed to you, we are using the GPT, but thanks to the LangChain, it's flexible. We can change and use other LLMs that we may want. And we know that using our implementation, we have a good starter point for the engineer, even without deep knowledge about the underlying meta models. For future work, the challenge that we can see here, on the use of LLMs to solve this kind of problem, our approach is somehow a single agent approach. We have one agent that thinks on the full problem. And we are seeing the machine learning, the LLM community, that what is the future looks like. We will work much more with multi-agent approach, which means that we will decompose the problem, but instead of solve the problem just using the LLMs as I showed to you, we will give these small problems to very specialized agents that will solve one part of the problem per time. With this multi-agent approach, we can also think on integration, what we call the human in the loop. It means that we can provide a more interactive approach. Now, with using our tool, the user provide the eCore meta models and the description and have the VPDL draft at the end, but we can think on something more interactive, like a chat. And we can also, we also intend to test using other prompt engineering techniques. As I mentioned before, the prompt templates are created by us. And the prompt engineering is a very empirically engineering. We need to try and a lot of possibilities. It's natural language text. We need to instruct the LLM to behave in some way. So we together with the chain of thoughts and the few shot prompting, we can try other prompt engineering techniques. On the AMD side, on the integration of everything on the modeling workbench, we can first think about a better integration between our solution and the EMF views, the Eclipse workbench, because now they are splitted solutions. The user needs to copy and paste the draft to the EMF views to use. And we can also try to find relevant data sets of model views. As you see now, we have 4 views that we are using to test, and also with these 4 views, we have some troubles to use good metrics. We are using precision and recall, but with a relevant data set with more views, we can think about use other metrics like the PSZK. That is one of the metrics that has been used to analyze code generation. That's it. Thank you. I'm open to answer any question, and on the QR code you have access to the code and artifacts of our work.
Thank you, James, for the presentation. Questions?
Thank you for the talk. It was very interesting. So one of the things I noticed is you did manage to have the LLM generate syntactically correct views and so on. But I think I also saw in one of the slides, I think it was slide 19, I think, where there was a bit of EMF views where it just had arbitrary natural text in it, was it? Which I guess you had to iterate through over it, right? So there were bits by on, right?
Yeah.
So I was just wondering if you had looked at things like output grammars for LLM. So this is something that it's not really a thing on GPT-4, but llama.cpp has output grammars. You can give it a Bacchus noun form of the grammar of your language, and it will limit the available tokens. So instead of asking, random words and so on, it will just say, well, according to the grammar, you can only pick among these ones. Which one do you want among the ones that are available? Have you looked into these?
Thank you for the question. Indeed, we look to this kind of approach. This is, I didn't include in the future work, but it's somehow a natural continuation of what we are trying to do here, exactly because we know that even with standard GPT, we are capable to generate OCL-like code. They are capable to generate something that looks like OCL, but you are right, to generate something that is more formal, we need to provide some grammar. And I was not aware about the Llama capabilities to do it, but thank you. Yeah, but indeed, to give a grammar to the LLM is indeed something that we need to try on the future.
Yeah, because it might be that one option might be to make saying, okay, I actually know a little bit of the generating arbitrary text, right?
Yeah. One challenge that I can see on the approach, I didn't try, but I can see because a grammar can be, if you give the grammar to the LLM, it will be a long textual file. And we are in our approach, we are giving to the LLM long files that represent the meta models. Yeah. So with the meta models plus the grammar, maybe we will have troubles with the context window of the LLM.
But it's actually not part of. It's actually the configuration of the LLM. So okay, I can show you a link maybe later during the break. I can show you a little bit of where to look at. Okay, but it's more a prompt to the LLM.
Okay. So this one I was not aware about.
Yeah, I can show you later.
Okay, thank you.
I was wondering about how many examples did you use for the few shot approach?
We have these results that we have here. I'm using 2 examples for the few shot, but we on the experimentations, if you look on the artifact, we have the option. So when the user will run, they can choose between one and five examples per view. It has a problem because with 5 examples, the problem that I mentioned right now also happens. We have a pretty long textual information that sometimes does not fit on the context window. But yeah, between 1 and 5. These results are 2.
Okay, perfect. And what about which technique was better, like few shot or cut? What was your experience?
Yeah, actually, this is a combination of both. It's a few shot chain of thoughts. No, yeah, few shot chain of thoughts. But I think that the few shot give us better results even without the chain of thoughts, even without the instructions of the chain of thoughts. So the few shots is better.
Okay. And could you elaborate a bit more about the data set used for this study?
Yeah, so we got some we got some views that we know from the literature. We have 4 views that were used in other papers. So what we did here, we have this reference code that we have the final VPDL. We extract the explanation of the view from these papers. So very naive explanation of each view, and we just give to the LLM. This is our idea. This is something that I didn't mention about, but we know that this is something that sounds standard for who is using LLMs. Better instructions give better solutions. So we know that our prompts are not our prompts. The user prompts are not the best ones because we are just extracting them from the papers. When we try to improve this prompt, we reach better results. But we are trying to be fair and also be reproducible. So this extraction looks like a very reproducible approach.
Okay.
Yeah, but the data set contains the core meta models, the user description, and the reference VPDL.
And was it for the same domain?
No. They are the 4 views are each one of a different domain.
Okay, perfect. Let's thank James again.
Thank you.
And before finishing the session, Ralph wants to say a word.
Thank you. Just want to remind you, there's an SLE dinner tomorrow on Monday, organized by Eric van Wyk, and we need to get numbers of interested attendees today by the end of the last session. I'm going to connect my computer. If you can, just email Eric van Wyk. But I will project one slide where is a QR code and a URL on. So please sign up by 7:30 today, and it's a nice dinner place. Eric was explaining it. Departure tomorrow is at 6 p.m. from the lobby, like 20 minutes walking, right? So probably starting like 6:30 with the dinner, so you can also go there by yourself theoretically. But please sign up for today. You can also bring your spouse, whatever. So I will project it now. Thank you.
Thank you everyone for attending this session, and let's see the QR code to get the dinner. Okay.
All right, welcome back everyone. Welcome to the first afternoon session on language design and implementation. My name is Thomas van Binsbergen. I will be the chair for the session. We are not looking at the slides yet. So we can get the slides up. The first presentation will be by Luca Miljak on concrete syntax meta patterns. The floor is yours.
In the title of this talk, let me first explain a bit of the context around it. So the context is automated software restructurings or refactorings. So we need to apply restructurings or refactorings to keep large-scale software maintainable. And you can think of examples like API migrations, like I'm switching a logging framework. That means I now need to rummage through millions of lines of code to find all the places where I call my old logger and then switch to that new logger. It's not feasible to do that by hand, so we want to do automated refactorings to accomplish that. But industry is still sometimes reluctant to apply automated restructurings. The obvious reason is, well, safety concerns. How do you know that after you've applied such an intrusive restructuring that it still has the correct behavior? But other reasons are, well, it's a big time investment. You need to hire or find a developer that is willing to implement this restructuring and then hope that they have even the knowledge to do so, because, well, the field of metaprogramming is not always that accessible to everyone. So in this talk, I will introduce a new technique that hopefully makes restructurings, writing your own restructurings, a little bit more usable than it's currently. So before that, let's introduce some background on solutions that already exist to make writing restructurings easier. And one of those solutions are concrete syntax patterns. Now on the top lines, you'll find some rewrite rules that apply some very simple restructuring. You have an assert true statement that checks whether two expressions are equal, and we rewrite that to an assert equals method. Now the E1 and the E2 in there represent meta variables that can represent any expression on which you match. And the example below that with an if statement, well, that matches on superfluous equals true statements you may have found in practice already. So we can also restructure that to remove the unnecessary equals true from it. Now this is concrete syntax because we reuse the syntax of the object language. And the object language in this case can be something like Java or, well, any language that supports this kind of syntax. Internally, concrete syntax gets compiled to abstract syntax. So at the bottom of the slide, you'll see the equivalent restructuring, but using the abstract syntax of the language rather than the concrete syntax. And I don't think I need to convince you that the concrete syntax is a lot more readable than the abstract variant. Furthermore, if you want to write the abstract syntax variant, you need to know the exact abstract syntax structure of the language that you're using, which, well, requires time, learning, and well, we'd rather use the concrete syntax. So concrete syntax is one way which we improve the usability of writing restructurings. Another method, another technique are called meta patterns. And meta patterns we just informally define as patterns that contain more than just terms with holes. So that's quite broad. There are some examples on the slide. So we have a disjunctive pattern where we can, well, say we can match on function calls that either match a functions named foo or bar. A descendant pattern below that. In that example, we match on function definitions of foo that anywhere in the body have a return statement that returns 0. So the / there indicates a descendant pattern. That means we are matching on that AST node or any of its descendants. Similarly, we can have sequence patterns to more fancily match on lists. But also, it can be more than just pattern matching. The pattern can also have some behavior to it, and that's what we can do with patches. So we can actually have some rewrite rule inside the pattern itself. And the example there at the bottom, we match on function calls to foo, and we rename that to bar. And the nice thing about meta patterns is that we now inline a lot of logic that normally would be outside of the patterns into the pattern itself, making the code a little bit more concise. So now I've introduced two ways to make restructurings more usable. One is with concrete syntax, and this with meta patterns. Now, the contribution of this work is, well, can we embed the meta patterns in the concrete syntax, which we aptly call concrete syntax meta patterns. We're going to try to compile these concrete syntax meta patterns to abstract syntax meta patterns. Those are the examples that I've shown on the previous slide. I'm going to do that using black box parsers. That means that all I need is some parser of the language that you want to use, Java, C++, whatever, and we don't care how that parser works internally. That compilation should just work. In this talk, I will show how we compile the disjunctive pattern. The paper also contains some more example meta patterns and how to compile those. So let's introduce some examples of what we can do with concrete syntax meta patterns. So here we have a pattern where this is not a meta pattern yet, this is just an ordinary pattern. We match on classes that have just some single function named foo in them, and that immediately returns some kind of expression. We can make this pattern a bit more interesting by adding a disjunction to it. Now we match on both classes and structs. We can make it even more interesting by making it a sequence pattern. So now I've specified that there can be an arbitrary amount of declarations above and below my function foo. We can make it even more interesting by adding a descendant pattern. Here I've specified that we match on code that, well, the return statement can be in any part of the body. It just doesn't have to be the only statement in the body. And we can keep on going. I can add a patch to it, so I can patch all return statements to, well, something else. In this case, I am wrapping some function called to bar around the expression that I'm matching on. And I can just keep on going. I can add another disjunction here where we have some kind of default case where if we match on a return 0 statement, then we patch that to return -1, and otherwise we do the other case. And the nice thing about this concrete syntax meta pattern is that, well, it's all the logic is contained in the pattern itself. It remains readable. Normally, all of this disjunction, the patching, it occurs outside of the pattern, which makes the content or the behavior of your restructuring more scattered than it normally is. Okay. In the remainder of the talk, I will try to explain how we compile this meta pattern, concrete syntax meta pattern, to an abstract syntax meta pattern. But before that, we're gonna do a background section because we are going to extend some previous work on compiling concrete syntax using black box parsers. So this has no meta patterns yet. This is just, again, terms with holes. This is based on a paper by Roden Aarse et al. On concrete syntax with black box parsers. And the idea, as I also mentioned in the introduction, is we're going to plug in some black box parser, and we're just going to hope that the compiler is going to work. Well, we're not going to hope. We're going to construct a compiler in such a way that it works with a black box parser. So again, the goal is on the left-hand side, you have a concrete syntax pattern. On the right-hand side, we have an abstract syntax pattern. How do we get from left to right with just a black box parser? Well, what they do is they first encode the pattern to some parsable string. And in this case, the example, we replaced the meta variable e just with 0, because 0 is some parsable expression. Now that we have a parsable string, we can actually invoke the black box parser, and that gives us an abstract syntax tree. And as a very last step, we can decode this syntax tree back into an actual pattern by reversing the parts that we have encoded. So we're gonna zoom this process in a little bit more detail. Let's start with describing the black box parser interface. So we require the following elements. We need a set of all the syntactic types of that the parser supports. So that can be an expression, name, statement, declaration, you name it. It depends on the language that you wish to support. Next, we of course need a parse function that's given a syntactic type and a string that we want to parse. We need to get the AST. And I've added a note here that the AST nodes should be annotated with location information. They'll become more clear later on. And lastly, we need a function named gen, standing for generate, that takes a syntactic type and generates some string for that type, some parsable string for that type. So for example, if we generate a string for an expression, we can just let it output 0, because 0 is represents an expression. So let's take a look at an example and go through everything step by step. So suppose we have this example and we want to we want to compile this to an abstract pattern. The first step is actually on the user side. We require the user to annotate each meta variable with its corresponding syntactic type. In this case, F should be a name and E is an expression. As a next step, we want to encode this, and that will turn our program into the following. So F gets, the meta variable F gets replaced by some name X, and the meta variable E gets replaced by 0. And that's where we use the gen function that I've introduced before. And the next step, as part of the encoding step, we need to remember everything that we've encoded. So the X was the meta variable F, and the 0 was from the meta variable E. We're going to call this the decoder, because we're going to use this in the decoding step. The numbers there on the bottom left represent the location information. So that is the location in the source string that we have parsed. So in this case, X occurred at index 4 and ends at index 5 in the string that we're going to parse later on. And we need the location information to uniquely identify those parts that we have encoded. So next step, we parse using the black box parser, so we get some AST out of it. And as a last step, we decode it. So we try to identify those parts of the AST that originated from encoded meta variables. So in this case, the name and the integer literal originated from the meta variables F and E, which we can, by the way, detect using location information that the black box parser gives us. And then we just replace them back with the meta variables we used. And this is the basic process from the paper, Concrete Syntax Using Black Box Parsers. Now, in our work, we're going to extend this compiler to also support meta patterns, and I'm going to show that by adding a disjunctive pattern. So here we have another example where we have a concrete syntax meta pattern. In this example, we match on if statements, where the conditional is the superfluous equals true condition, or, well, the symmetric variant true equals some expression. So the @ symbol indicates the disjunctive operator in this case. Again, we're going to do the exact same steps, but this time we're going to treat the entire disjunctive pattern here as if it was some meta variable. So we let the user annotate this disjunction with some syntactic type. In this case, the condition of an if statement is an expression. Next step, we encode the entire thing. So we replace the entire disjunctive pattern with 0, because expressions encode to 0. Again, this is our corresponding decoder, so 0 gets decoded to this entire disjunctive pattern. Next step, we parse. Then we decode again, so we identify all the parts that originated from encoded elements. We replace them with the original meta patterns. And as a last step, we still need to recursively compile the left and right disjuncts of the disjunction. And then we get the following abstract syntax meta pattern. Now, hopefully that made sense, because we're going to make this a little bit more interesting, because we're going to now introduce the inferred disjunctive pattern. As I said, the first step was that the user required to annotate the meta pattern with a type. That is a bit annoying because it clutters our pattern, but also the user now needs to think about, oh, what is this type? But it's something that should not be necessary. So can we infer this type instead somehow? So we're going to do the exact same thing again, but we're going to skip step 1. And we're going to try to encode this. And we can actually very easily encode this without the type, because we can actually just take either the left-hand side and the right-hand side of the disjunction and use that to encode our entire pattern. So I can take the E equals true and use that as our encoding for the meta pattern. Yeah, so we can use the left or right disjunct, and we replace the entire thing with 0 equals true, which represented the E equals true part from before. And now our decoder is a little bit larger because it includes the 0 equals true part. Again, we parse it. We go through the exact same steps. What is happening? Yes. We're going to parse, and we're going to decode again using the same process, and we get the exact same thing back as we had before. We then recursively compile the disjuncts, and well, we get the exact same pattern as we had before, except this time we did not need to annotate it using the type. So that was the disjunction. In the paper, we also introduced some other meta patterns where we describe the compilation behavior. I'm going to go over them very briefly with as much time as I have left. So we have actually 2 variants of the disjunctive pattern in the paper. We have a context-free variant and a context-dependent variant. The example I've just shown you used a context-free variant. The context-dependent variant, one use case for this, well, I've written down here, is if you want to pattern match on either classes or structs. And behavior of this meta pattern is that we literally unfold every single case here. So we have well, the class foo and the struct foo. We take the entire program and unfold it in its entirety. And this is context dependent because we now take the entire context of the program into account. Why is this useful? Why do we want this over the context-free variant? Well, it's useful if we have no location information. So in practice, we have found that often external parsers that we use, they don't provide location information for every node in the AST, and particularly for keywords. So if I have a class and a struct node in my AST, that sometimes does not have location information, so we cannot decode them. And therefore, we just take the entire program and parse that part. There's one downside to the context-dependent disjunction. That is that we can get an exponential blow-up if we use it too often in one single pattern, because we need to consider every single combination. So if you have an A or B followed by a C or D, we need to consider every single combination of that, so AC, AD, BC, BD, and you can imagine that if you use this a lot, well, there's a lot of time that you need to compile this pattern. Luckily, again, the use cases for this are limited. We're mostly using it to compile keywords. because those have no location information. Another example pattern in the paper is the descendant pattern. The example on the left-hand side is a descendant pattern where we try to match on recursive function definitions. So we have some function definition f, and at any position in the body of f, we look for a function call to that same f again. This is an annotated variant, as in we had to specify the type of the descendant pattern. Well, the descendant pattern represents a list of statements. Furthermore, we needed another type expression that represents the inner type, the type of the inner expression, so the inner pattern. So that's the function called to f. That is an expression, therefore we need the expression annotation there. There's an inferred variant of this that we also introduced in the paper, where we get rid of the outer type that you need to specify, so we can get rid of the statement list here. It's not a nice solution, but it works. Because we need this outer type to generate an encoding, but we can also just try to guess the encoding using some hard-coded set of guesses. So we can, for example, try to guess A, but that's not going to parse. What we can do is we can fill in integer A followed by a semicolon, and then this entire pattern is going to successfully parse. Again, a problem with guessing it in this way is that we get an exponential blow-up if we have many descendant patterns, but in practice we have not encountered examples where we need more than a few descendant patterns in one single pattern. And there's also ways to mitigate it, so we can keep this guess set very small. We can, well, in this example, the A and the int A, they already represent a wide variety of syntactic types that we have. So the A in like a language like C++ represents an expression, it represents a name, it represents a declarator. The int A represents statements, declarations. So we already cover a wide variety of syntactical constructs just by these two guesses. Okay, now going to conclude the talk by summarizing. So we've introduced concrete syntax meta patterns. We like them because it's a very declarative way of metaprogramming. We specifically applied it in the context of software restructuring. We have disjunctions, descendant patterns, and patches. This is not an exhaustive set of meta patterns, but we do believe that this is a representative set. So if you want to add more meta patterns, you can use a similar technique to compile them using one of those. We compile them using black box parsers. This allows us to easily support new languages without too much effort. And we even improved the notation of the meta patterns by using inference on the types. In the paper, there's a more formal presentation of the compiler. Furthermore, we've implemented the compiler and concrete syntax meta patterns as a Kotlin library, and we support C++. So we've implemented the black box parser interface for C++. Furthermore, we have some discussion on several elements. You're also welcome to ask questions about those. So we discussed the effort to implement new meta patterns. We discuss how much effort you need to implement the black box parser. We discussed the problem of the exponential blowup, and how expressive and applicable context syntax meta patterns are in general. So with that, I conclude this talk. Thank you for listening. Are there any questions?
We have about 5 minutes for questions.
Thank you. Maybe I missed it. It seems to me that decode could lead to ambiguities, right? Where you introduce a 0 for an expression, what if there already was a 0?
So we use location information. So we uniquely identify the position in which it occurs in the string that we're parsing. And we hope that we assume that the black box parser also gives us location information for each node in the AST. So we use location information to disambiguate and uniquely identify each AST node.
Is that guaranteed to always work, or are there corner cases?
So there are cases when there can be two AST nodes with the same location. We discussed this in the paper, the default case is that we always take the outermost node because that represents the most general type, so to say. So, for example, declarations are also statements in a context-free grammar. So you can have in your AST, you can have a declaration statement and then then a declaration. Those are two AST nodes that have the same location. We always take then the outermost type.
That's when parsing actually discovers an ambiguity, right? But what I meant is when the expression already contains a zero and then you have a meta pattern E, which you replace by another zero.
So then you will have two zeros in your AST that have two different locations. So there's two different zeros.
Hi, thank you for the talk. I was curious about, so there are some languages where the return position in a function is not indicated with a keyword return. It's just kind of the last position in an expression, or all the last positions in all the branches of a conditional. Have you encountered any situations like that, and how would you handle that?
We have not encountered situations like this because we've mostly applied it on C++. C++ does have other ambiguities, but we have not run into those with the examples that we've run. There are ways to mitigate this, so you can. So this would be an ambiguity. So a piece of code can represent multiple syntactic types. The way you could resolve that, which you have not implemented yet, so that's future work, is letting the user explicitly specify the type that a piece of code, the syntactic type that a piece of code has. So then you can explicitly specify, oh, this is supposed to be a return statement or something else. But again, that's not, we currently don't have that, but that would be a way to solve it.
Okay. I have another question. Someone else can go first. Okay, so this is maybe more about future work, but I was curious how you handle scoping for if you're trying to do refactorings. There might be multiple functions called f or foo or whatever in a code base. Do you fully qualify them as a pre-processing pass, or is there some more clever way to do this?
That is a very good question. At the moment, everything is purely syntax-based with these concrete syntax meta patterns. We are working on also supporting meta patterns where you can specify, oh, this f has to reference this function definition f. So you can be explicit about which reference is supposed to reference which declaration. So that also takes then the static semantics of the language into account rather than just the syntax.
Okay, thank you.
So I was wondering about these two different kinds of disjunction, because you just presented that you're putting a lot of effort into inference so that there's less clutter around these types, which kind of refer to the abstract syntax again. But now you have this really an implementation detail leaking into your patterns, right? Because why would I care as a writer of these patterns whether it's context free or context dependent? Can you infer that?
Yeah, that's also a valid point. One solution from a user side would be to just always use the context-dependent disjunction and hope you're not using too many of them to cause too much of a performance blow-up. In general, we have found that the context-free disjunction almost works everywhere except for keywords. And I think that is something that can be easily taught to someone using concrete syntax meta patterns. But I think this is a fair point. But this is unfortunately not necessarily a problem with the design, but well, it's an edge case that we are able now to support with, and we are allowed to support new black box parser with it. That we are to support black box parsers that do not give location information for every AST node. So it is indeed an implementation detail, but we find it a necessary one.
Final question from my side, maybe while the second speaker sets up. So given that you are from Delft, I wondered whether this is planned to be integrated in SpoofX.
Oh, that's a good question. There's no plans at the moment to integrate it in SpoofX, but there's definitely talks about it. We can discuss more later.
Maybe we'll find out more next year. Yeah, yeah. All right, let us thank the speaker one more time.
Should be connected. Yep.
All right. Our second speaker is Idris Ryuak, who's going to talk about efficient evaluation of fixed-point attributes in the context of attribute grammars.
Yep. Thank you. So hello, everyone. My name is Idris Ryuak. I'm a PhD student at Lund University in Sweden. And yesterday I will talk about the efficient demand evaluation of fixed-point attribute using static analysis. Can you hear me now? Yeah, better. So this is a joint work with Niklas Forsch, Jesper Åkvist, Jorre Ledin, and Christoph Reichenbach. So static analysis is everywhere. And I hope you agree with me. And we can use static analysis to detect common bugs. For example, this piece of Java code is supposed to compute the nth number of the Fibonacci sequence. But with a good static analyzer will tell us that the assignment at line 6 is actually never used. So there might be an error here. Or, like for example, if we consider this other example, depending on the value of b, we might have a null pointer exception at line 4. And ideally, we would like to have a static analyzer that helps us to detect these kind of bugs while we're writing the code, and we don't have to wait, so that we don't have to wait like a couple of hours before getting the feedback from the static analyzer. And in order to do so, we need a static analyzer that is not only fast, but it should be able to evaluate the code in a demand-driven fashion. So demand-driven is, well, basically we just analyze what we actually need without computing the results for our entire code base. And it's basically the opposite or the dual of exhaustive evaluation, where we compute all the data even if it's not required. So like think of yourself, you are in front of your editor and you want to analyze your compilation unit. You don't have to analyze the entire code base, but just the compilation unit or the method. And we used JustAdd, which support a formalism called reference attribute grammars, which is both declarative and it inherently support demand-driven evaluation. So what is an attribute? Well, attributes were first introduced by Donald Knuth in 1968, and then they were extended to the object-oriented paradigm by Jorre Ledin. And let me explain you what is an attribute with an example. So again, let's consider our buggy Fibonacci example. If we parse it, we get this abstract syntax tree. And on top of this abstract syntax tree node, we can attach property, like we can derive properties. For example, let's say we want to know if this assignment here is dead. And by collecting information using other attributes, we can figure out that this assignment here is actually dead. And well, I said I use JustAdd. It supports reference attribute grammars. Example of project that use JustAdd are XtendJ, which is a Java 11 compiler. IntraJ, it's a static analyzer for Java 11. We have Blocky, we have Gem Modelica. But the main idea is that given a reference attribute grammar specification, we pass it through the JustAdd meta compiler, and what we get is the evaluation code. So the evaluation code is our actual XtendJ or our actual IntraJ. So let's go back to static analysis. Let's say we want to implement data flow analysis. And if we open the Dragon book on the chapter about data flow analysis, we will find this equation here, in and out equation. Those are equations for a backward data flow analysis. And if we look at the dependency between the function that we have in this equation, we found that in depends on gen, which and depends also on kill. It depends on out. Out will call the successor, so it will like construct the control flow graph somehow. And it will also call or depends on in. And now that we have in and out, we have somehow to figure out and like to interpret this information that we have in these in and out sets. And for example, we can use a function or like an attribute to figure out what is in this out set. So we can use that to figure out if a variable or if an assignment is dead. And each of these functions can be implemented as an attribute. And this one is a static call graph, static dependency graph of the attribute relation. But if we consider an instance of this one, we will have many more attributes many more instances of in and out and is dead. So if we go back to our Fibonacci example again, we have the abstract syntax tree, and on top of that we can put this in and out in order to compute our data flow analysis. And I don't want you too much to focus on the details of this example here. I want you to focus on the shape of this graph. So if we look at in and out, this one. That in depends indirectly on itself. So we have a cycle. And in order to compute the value for that in, we have to compute a fixed point. And we can do that with reference attribute grammars by using circular attributes. Circular attributes are attributes which value may depend directly or indirectly on itself. And well, they are computed using this fixed point computation. We start with a bottom value, and we keep iterating until we reach a fixed point. Now the question is, how can we efficiently compute a demand-driven fixed point attribute? And well, it's not easy. There has been a lot of research on how to compute circular attributes. The first, in the original attribute grammars, circular attributes were not allowed. And then Farrow and Jones, independently, they introduced the concept of circular but well-defined attribute grammars. Boyland, in 1996, he presented he described how to compute circular attributes in a demand-driven fashion. And then Sasaki and Sasa, they described how to compute them for remote attributes, which are like a sort of reference attribute, but the reference are computed at compile time. And in 2003, Magnusson introduced the first algorithm for computing for circular reference attribute grammars, which is called the basis stack. In 2017, Åkvist presented the relaxed monolithic, which is an algorithm that is supposed to overcome the limitation of the basic stack. And today, I will present the relaxed stack, which overcomes the limitation of the relaxed monolithic. So since everything is built on top of the basic stack, I will start from there. So the basic stack allowed the coexistence of two different kinds of attributes: circular attributes, which the trigger a fixed point computation, and non-circular attributes, which are evaluated. And once they are evaluated, fully evaluated, they are immediately cached and are ready to be reused. And the user or the developer has to annotate all the circular attributes manually. So if we consider our example here, the user will have to annotate both in and out, and everything that is not circular will be treated automatically by the compiler as non-circular. And this approach, or this algorithm, has two main limitations. The first one is that some attributes exhibit this circularity behavior for very few input. For example, in the XNJ Java compiler, the type attribute that we use for type analysis is circular only for few constructor, for the lambda expression, but we will still pay a very expensive fixed point computation to compute the type analysis. And the second thing is that it becomes infeasible for very large projects. So here we have a snapshot of the XNJ Java compiler call graph. Each red dot is a circular attribute, and you can think about changing a single attribute may cause the changing like the circularity of other attributes. So it becomes really easy to introduce errors. And so Åkvist, he tries to overcome this limitation by introducing the relaxed monolithic algorithm. This algorithm allowed the coexistence of two attributes, again, circular, which trigger fixed point computation, but this time there has to be at least one attribute labeled as circular in each cycle. So we don't have to annotate everything, we just have to have at least one circular attribute in each cycle. And then instead of non-circular, we have agnostic attributes. Agnostic attributes, they behave as non-circular if they are evaluated, if they are not called inside a circular evaluation, and as soon as they are evaluated inside a circular evaluation, they become circular. So they behave as circular. So for this example here, the user will have to annotate one of the two attributes between in and out. Let's suppose decide to annotate in. And then everything else will be treated as agnostic. So we will have everything treated as agnostic. And everything works except that as soon as we have many circular attributes, it becomes inefficient. So the problem is that the algorithm cannot recognize, so as soon as we start with a circular attribute, or as soon as we encounter a circular attribute, all the downstream attributes will be treated as circular, even a diagnostic one. And this implies that we will compute everything, the circular evaluation in a big monolithic fixed point computation. So if we go back to our example here, we have the example as before. Allow me to extend it a little bit where we introduce two extra attributes, is reachable and reachable, like to remove everything that is not reachable, let's say. Reachable is a circular attribute, and is reachable is an agnostic one. So now let's suppose that the first component with two attributes will require 20 iterations to converge, whereas the second one will require only 10 iterations to converge. And let's suppose that we query is dead. So here in green we have things that are evaluated once, and in red we have things that are evaluated 20 times. We start with is dead. Is dead will call out, that will call in. In here is a circular attribute, so from now on the algorithm will treat everything as circular, and everything will be computed in this big monolithic fixed point computation. So everything will be computed 20 times, re-evaluated 20 times. So the gen will be computed 20 times, kill 20 times, even if they are supposed, like they are non-circular. So that's a huge waste of resources. So we propose, okay, and then we have isDead, which is then once everything is finished, that's cached immediately and returned. So that's computed only once. So we propose a new algorithm, which basically combines and allows the coexistence of all the three kind of attributes. So we have circular, non-circular, and agnostic. So the basic stack algorithm was able to decompose this static strongly connected component in a smaller fixed point. But the annotation effort was high and made it impossible to build big projects. The relaxed monolithic, on the other hand, the annotation effort was very low, but inefficient in the case of many strongly connected components and circular attributes. So our algorithm can handle can decompose these strongly connected components, but what about the annotation effort? Well, it's slow with the use of static analysis. And the key idea is that if we know that a circular or an agnostic attribute labeled as circular or agnostic attributes are not in a circular evaluation, they will never appear in a circular evaluation, then we can treat them as non-circular always. And I will give you an overview of the pipeline. So we start again with our reference attribute grammar specification. We pass it to the just add meta compiler that will generate the evaluation code. And so far, those are the same steps that we will do normally. Then we take an extra step. We pass the evaluation code to the CAT tool, which is the call graph analysis tool. From this tool, we'll find out what is circular and what is non-circular. And it will output this metadata file containing this classification of like all the attributes that are non-circular. And then we pass it again to the same just add meta compiler plus some flags that allow us to read this metadata file. And we generate the optimized evaluation code. So going back to our example, so as I said, we start from the Java code that is generated by JustAdd. We construct the call graph, and this is the call graph, let's say. And then we compute the strongly connected component to find out which attributes are non-circular. And the idea is to find out all the trivial strongly connected components. So we have that is a trivial strongly connected component. This one is not a trivial component, and so on. So we have two non-trivial strongly connected components, but for everything else, we can just safely change the label from agnostic to non-circular. And then if we go back to our example where we have the two components that one will converge in 20 iteration and the other one in 10 iteration, and we query is dead. So we start with is dead, which will call out, that will call in, and then gen is non-circular, so it will be immediately cached and returned, so it will never be computed again. Kill, the same for kill. Then the successor will call is reachable, and this one is a special attribute because it's a non-circular attribute that calls a circular attribute. And this one will stop all the ongoing evaluation, allowing to start new fixed point attributes, new fixed point computation. So this one will converge after 10 iteration. So now is reachable can be computed, fully computed, and the same for the successor. So in and out will converge after 20 iteration, and is dead in one. So now we have like the optimal solution where we don't have waste of resources or like, we don't compute things multiple times. Okay. So we conducted some experiments. So we compared the existing algorithms with our new relaxed stacked algorithm. And we didn't change the specification of the analysis, so we kept the same reference attribute grammar specification. And we did 3 case studies. Here today I will present only one. You can find the other 2 in the paper. But the first 2 I've shown, those are non-circular application, and they have shown that our algorithm does not introduce overhead. So it's sometimes faster, slightly faster, but not significantly faster in this case for like applications that are not heavily circular. And then for the IntelliJ static analyzer, which is a heavily circular application, we have the following result. So here the idea is that we compute the intraprocedural null pointer reference analysis for Java programs. And we computed the analysis on 8 different projects, starting from Antler, which is like 40,000 lines of code, to POI, which is 300,000 lines of code. And we measured both startup and steady state. And for startup, we have a speed up between 7x to 115 with a median of 15x. And in particular, like for XNJ, we have that it took for the relaxed monolithic 1,500 seconds. And that's because there was a method that was big, like 6,000 line of code, and it didn't scale for the relaxed monolithic algorithm. And then for steady state, we have similar result. We have a speed up between 16x to 35x, and the median is 22. And we had to introduce a timeout there because otherwise the computation would have been, like the evaluation would have took so long. And what about the demand-driven scenario? We also considered that because that was what we were interested in. So we randomly selected 10, 20, 50, 100, and 200 methods from each of these projects. And here we have the results from PMD. And we can see that for 200 methods, we managed to pass from 1.2 seconds to less than 0.2 with a speed up of 11x. And the results are proportional with the whole program analysis. Yeah. So to conclude, we introduced this new relaxed stacked algorithm. And then we use static analysis to reduce the annotation effort. So now we automatically find or reclassify circular and agnostic attributes to non-circular. And yeah, we compared the results with the basic stack and the relaxed monolithic, and we found out that for heavily circular application, our algorithm is faster. And we don't have to change, so it's completely compatible with the existing RAG specifications, so the user doesn't have to change anything. And in the future, we plan to consider dynamic, like keeping track of dynamic strongly connected component, and also considering more advanced static analysis to improve the precision. And yeah, that's it. Here there is a link to the paper and a summary of what we did.
We have plenty of time for questions.
Cool work.
Yeah.
I really like how you were able to just reuse some tooling and apply it to the generated Java code to get the metadata that you needed. But what's the cost? Because you are first compiling your spec entirely, then you're analyzing the Java side, and then you're compiling it again.
Yes. So that's a good question. So we haven't looked at that aspect. We believe that, I mean, to get a speed up in the actual runtime, the user is like, can spend an extra minute or two in order to do this extra step and this extra analysis. And the user doesn't have to do anything, so it's completely automatized. And I think that's something that, I mean, you do it once per release, and then it should be doable, I think. But that's a good question. We should definitely look into it.
Thanks. It was a nice talk. So I was knowing a little bit about JSTAT. I was very curious where the static analysis was coming from, and it's from this external tool. I was secretly hoping that you had invested time to do analysis on the attribute grammars, but I know the whole point of demand-driven evaluation is you can just skip all that stuff. You don't have to worry about ordered attributes and all that sort of stuff. So I was like Jeff. I thought it was a very nice way to sort of handle it. But I'm curious about. I had two questions. So one is, do you lose any accuracy by doing the analysis on the generated Java code, that somehow, you know, you lose some information in the generation of the Java code and the analysis there is not as precise as it might be if you did it on the attribute grammar code?
Yes, I think we don't lose precision from that side, like from the grammar. Okay, we could use some information that we have in the grammar to improve the precision. And sometimes we just do recursion on the tree and we don't have cycles, but our static analyzer, like the call graph analyzer, we consider that as a cycle. And so we could use information from the grammar to like improve the precision in that sense. Or like even considering a more advanced static analyzer, like instead of, right now we do class hierarchy analysis, very simple analysis, like doing some alias analysis would improve quite a lot the precision. And I think this example of the recursion on the grammar on the tree will be solved by much more precise analysis. Yeah.
Oh, thanks. But I mean, you still have great speed up, so it's not like you've suffered. So my other question was more general about circular attributes. When you talk about fixed points, are these always least fixed points, or is there a sense that the value in the circular attribute is sort of monotonically growing in some way, or does that not sort of come into the discussion?
Well, if an attribute is labeled as circular, then we will start this fixed point computation. And we require the user to have a monotonic transfer function. And all the elements have to be all the partial values have to be in a finite lattice. So those are like a constraint that we put on the developer. So yes, as soon as we encounter a circular attribute, we will start a fixed point computation. Might be a trivial one, like if we do reachability, for example, that will be converging once, like one iteration. But yeah, we will always start a fixed point computation. Yep.
You have to forgive me. I did not listen to the full talk. I've seen the abstract.
Yeah.
So I had a question on what type of analysis can you support? Do you support, say, analysis which have infinite lattice, like say constant propagation with distributive properties, or say range analysis which has an infinite lattice both sides?
So Justad was born as a metacompiler, so it was not built for like constructing analysis or static analysis. But now we are going more towards in that direction. So now we support circular attributes, and we can do analysis on finite lattice.
Will it support, say, an analysis which is non-distributive?
Which is not, sorry?
Which is non-distributive. Non-distributive, say,
yeah.
Constant propagation analysis is non-distributive, right?
Yes, I would say so, yeah, that should work.
Okay, because the traditional IDE type of analysis may not be able to support those. So just curious with that.
That's a good question. To be honest, I don't know, like on top of my head.
Any more questions?
So I have a final question.
Yeah.
Actually, I have two questions, but I think the answer boils down to the same thing. So first of all, I observed that because you're computing the strongly connected components, you're identifying the cycles.
Yeah.
So you're identifying the circular attributes.
Yeah.
So my observation would be that you don't need this kind of labeling, but at the same time, not every circular attribute would compute a fixed point. So is the latter the reason that you still decide to ask a user to identify circular attributes?
Yes, actually, that's a good, yeah, exactly. I mean, otherwise, if we do everything automatically, we might introduce overhead, and we might be less precise than the user.
And just non-termination, I'm thinking.
Once again?
Non-termination, potentially.
Well, okay, the user also has to specify this bottom value. Without the bottom value, the Justad compiler cannot find out what's the bottom value. And that's one reason. Let's see. I would say that's the main reason. And the performance also, like, yeah.
All right, thank you very much. Let's thank our speaker one more time.
going to change?
Our third and final speaker is Laurent Huberdeau, who's going to talk about the design of a self-compiling C compiler POSIX shell.
So my name is Laurent Huberdeau, and I'm here to talk about Peanut, C transpiler targeting human-readable POSIX shell code. So this is work I'm doing with Cassandre Hamel, Marc Philly, and Stéphane Monnier from Université de Montréal. So first we'll see what Peanut is, then quickly go over some of our motivations, then some of the implementation and its challenges, and see how it works. So this is Peanut in one slide. So on the left we see perfectly valid C code, and Peanut takes that and generates corresponding POSIX shell code. And then we can see that the put s function here takes a string pointer and iterates on it and emits each byte to standard out. And on the right, the shell code has the same structure, so the function name is the same, the local variables names are also the same. The while is compiled to a while loop with car to a put car call, and so on. And so this is what we mean by human-readable POSIX shell. And so a valid question to ask is why. Like generally, when you use C, you want performance, you want to be close to the hardware, and POSIX shell offers none of that. But there's one very specific use case where it's relevant, and it's for reproducible builds and bootstrapping. So we care about bootstrapping GCC, and there's this famous lecture from Ken Thompson where he described a compiler that was malicious, and the compiler would detect when it was compiling another compiler and inject its malicious code into the resulting binary. And the point that Ken Thompson was trying to make is that detecting such an attack would be very difficult because the compiler binary is opaque. It may be multiple megabytes of machine code. So really it would require a lot of work to detect that. And so in our case for GCC, if we want to compile it, we cannot just use any version we have on our machine because that version, we don't necessarily trust it. It may have some malicious code hidden in it. And so if we try to escape the malicious code of our version of GCC by recompiling it, the resulting binary would not be better. And so we're not the first people to attack this problem. There are like a stack of projects that try to reduce the size of the binaries required to bootstrap GCC as much as possible. And of course, like you always have to trust the layer under you, so like you have to trust the hardware, and then you have to trust the operating system, and then all the compilers that lead you to GCC. And so there's a very minimal operating system that's about 4 kilobytes of machine code that can be used to run a very minimal assembler called hex0 that's only 190 bytes. So in principle, these two blobs could be audited in a reasonable amount of time. And then these can be used to build up an abstraction until the MES-CC compiler is reached that's able to compile TCC and GCC. TCC is the tiny C compiler. It's about 10,000 lines of code, and it's able to compile an old version of GCC. And so once you've reached TCC, which is a reasonably easy target, then you can reach GCC. And then what's special about POSIX shell for it to be useful for bootstrapping? So really it's two things. The first is that it has many different implementations, and it's available on almost any platform. So for example, like almost everyone surely knows the bash implementation, but there are others like Corn shell, Ash, Dash, Z shell, and more. And they are so old that they were probably developed independently, and it also shows that it's a very stable platform, which means that it's the ideal candidate for double diverse compilation, which is a technique with a fancy name that's basically just using different compilers that you don't necessarily trust, doing the full bootstrap with them, and then if you get the same executable at the end, then it tells you something about the two compilers you used at the beginning, either that they are compromised in the same way, or more likely that they are uncompromised. And then because PostgreShell is relatively high level, it should be easy to read the code and see what it does. And so our plan is to have two compilers. The first one is Peanut Shell. So it takes a certain subset of C and turns it into human-readable PostgreShell code. And then obviously, because GCC and TCC use certain constructs of C that cannot really be mapped to PostgreShell, we have a second compiler called Peanut.exe that supports this larger subset of C and sends it to binary code. And so we can see that Peanut bridges the gap from the shell to GCC, which represents a world where, like, once you have GCC, you can compile basically everything. So here we can see how we would use such compilers to get to GCC. So they're both developed in C. So first we need to compile Peanut Shell using an existing C compiler. Here we use GCC. And so we get an executable version of Peanut Shell. And then we can recompile Peanut Shell and get a shell script version of it. So now at this point, we require the use of a PostgreShell implementation to run our script. And then we can continue and compile Peanut.exe. And then from Peanut.exe, we still need to have a shell, and it can be quite slow and limiting, and we want to use the shell as less as possible. And so we can recompile Peanut.exe to finally escape the shell and get a binary version of the Peanut.exe compiler. And then it's just a matter of compiling TCC and GCC, and we've won. Not quite. So if we look at this diagram, there are a few things that are wrong with it. So first, we have to use like a version of GCC that's like precompiled, so we're not able to trust it. But this is fine because there's nothing stopping us from reading the Peanut shell script and ensuring that it doesn't contain any malicious code. And then we still need to use other existing binaries, the PostgreShells. But then because there are just so many implementations available on almost all platforms, we can easily use many of them and do double iris compilation to make sure that they're not compromised. And then because like auditing the Peanut shell script will take some time, we don't want to do that every time we compile. So we only want to do that once. And then all you will need to compile GCC would be a PostgreShell implementation, the Peanut shell script, and the source code for the other compilers. So having said that, we still have to compile C to PostgreShell, and there are a few challenges ahead. So there's 3 big challenges. The first one is that PostgreShell doesn't offer arrays or data structures. All you have are strings, and you don't have ways of indexing into strings. So we'll have to work around that, especially to implement the heap. And then the shell functions are not able to return values or have local variables. So that's another thing we'll have to take care of. And then in C, I/O is done generally on a character per character basis. And in shell, it's much more line-based. So we'll have to convert from one to the other. So there's, oh, and on top of that, we also have other design goals. We want to be human readable. So we have to preserve the structure of the C source code as much as possible. Not use eval, because whenever you encounter eval, you could execute arbitrary code, and that would make auditing very difficult. And verifying constants and magic numbers would be very tedious, so we want to avoid them. And because we want to reduce the amount of pre-built binaries we have to trust as much as possible, we don't want to use any external utility, so no use of BC for arithmetic or OD for reading files, and be sufficiently fast for bootstrapping. So PostgreShell has one feature that really saves us, and it's arithmetic expansions. So generally, it's just to evaluate signed integer expressions. So if we wanted to evaluate 5 times 10, we would wrap that in the $parentheses syntax, and it would expand to 50. And it can also refer to variables. So those are environment variables. So you can refer to, for example, a plus and add it to 10. And fortunately, PostgreSQL supports all of the C arithmetic and logical operators. So this is very convenient, especially for assignments. So we can assign to new variables, and even those that were not previously declared. And that means we can assign the memory locations, the environment variables prefixed with underscore and then the address. So the first memory location will be _1, then _2, and so on. And to index, we can simply nest the arithmetic expansion in a way that constructs variable names dynamically. And so here, for example, if we want to dereference the memory location at address 2, we use two arithmetic expansions. So the first one contains x equals underscore, and then we open a second arithmetic expansion that will expand to 2. And so the outer expansion will execute x equals _2, and so read that memory location. Sometimes you want to ignore the result of the expression, so you'll see that syntax in some of the example where it starts with colon, it just ignores the result, but it still evaluates the expression. Generally, this is for assignments. And so bringing back the put s example from the beginning, we can see the while loop condition dereferences s, checks if it's 0, so if it's the null byte, and if it's not the null byte, it will emit it to standard out. And in shell, we can see we have two arithmetic expansion to dereference s, and we compare the result to 0. And if it's not 0, then we keep going and call the putCar function, again passing it the value of the byte. So that takes care of the first implementation challenge. And now that we have a heap, we can build data structure, so it helps with the other two. So we can extend shell functions and kind of match the C syntax of where you capture the result of a function call. So if you want the result of a function, you can see you write answer equals the function call. And in shell, what we do is every function has as its first argument something we call the return location, and it's just the name of the variable where we want the result to be in. So we can see the meaning of life function. What it does an arithmetic expansion where the left-hand side is $1, and $1 refers to that return location. And so if we want to call the meaning of life function and get its result in the answer variable, we just have to give it as its first argument the answer string. And so we can see it reads almost naturally. So instead of being on the left, the return location appears on the right, but the transformation is very natural, and like there's nothing surprising with it. And then for local variables and parameters, we just use a callee save calling convention. So whenever a function wants to use a variable, it first has to save the value, and then before returning, it has to restore the value of the variable. And we just we give nicer name to these push and pop operations that happen on a stack. So let pushes the value of a variable and initializes it, and then end let does the opposite at the end of a function call and restores the original value. So that can be a little bit slow because for every local variable you have a shell function call. And so fortunately there's an alternative implementation where there's the set command where you can change the parameter of a function dynamically. And so we can use that to add more parameters to the function call and store value that way. This is much faster, but it's much harder to read, and we ended up not having to use this optimization. But it's nice to know that it exists. So that takes care of the second challenge. And then for character-based I/O, Shell has file descriptors, so that's very convenient. And it has two built-in. The first one is read, that just reads a line, and then printf that can output any byte. And so with those, we can relatively easily implement the Unix open read and write functions. So we just have to buffer the read calls to read lines and then only feed the characters as they are needed. And that completes the implementation challenges. So we still had other design goals. So let's look at those again. So is it auditable and human readable? So far we've preserved the structure of the C source code. We haven't used eval. Instead, we've used arithmetic expansion as a limited or restricted eval that's still auditable. But we haven't really done anything regarding constants and magic numbers, so we'll have to get to that. We haven't used external utilities for arithmetic or I/O, and we're sufficiently fast for bootstrapping. We'll see later a table with a few times with some benchmarks. And so for avoiding magic numbers in C, really there's two sources of magic numbers. The first one are character constants. They don't exist in shell. And so instead of replacing the value of character constants with their ASCII code, we just define global variables that are read-only to give a name to these ASCII codes. So if you refer to the character A, really we'll replace that with a reference to the shell variable __A ___. Kind of looks like quote. And then for structure field offsets, we do the same. So the first field of a structure is at offset 0. The second one is at offset 1. And we do the same thing for the size of the structure. So whenever you access, so to read or to write a C structure, we just refer to that variable. And then another source of constants in C are string literals, and they don't have the same representation in C and in shell, so we have to convert from one to the other. And so we do that using the def string function. And so whenever we encounter a string literal, we add a def string function call before that initializes the string, so unpacks it into memory on the first time it's used. So does it work? Can we actually implement a reasonably large subset of C in POSIX shell? The answer is yes. So this chart shows the C language support that both of our compiler has. So Peanut shell supports function declarations, of course, if, switch statements, all the loops, structures, enums. It can do pointer arithmetic. It has dynamic memory allocation, some basic I/O functions, and a C preprocessor. And then Peanut exe extends that with switch, fall through, gotos, the address of operator, stack allocated structures, and so on. And then to compile TCC, there are things we don't yet support. So those are, for example, floats and unsigned numbers, bit fields, function pointers, and variadic functions. But it should be relatively quick to get there. And then more results. So as a rough measure of readability, we can compare the C source code size to the shell source code size, and it's about 35% larger, so not too different. And that includes like hard-coded runtime functions. So in practice, the difference is even smaller. Also, Peanut shell can compile existing programs we haven't written. So it's proof that some C programs use the subset we're targeting, and the code we generate can work with a very old version of Bash. So we can use the version 2.05b that comes from 2002. And in terms of bootstrapping time, to compile Peanut exe using the Peanut shell script, it takes about a minute, more or less, depending on the shell. There's Z shell that stands out. For some reason, it's much slower, but it is still very reasonable, especially for something that would only happen once. Like, right when you have compiled Peanut exe and TCC and GCC, you no longer have a reason to use Peanut shell. And then, so in conclusion, Peanut shell is a viable compilation target. We're still working on TCC to eventually be able to compile it from the shell. And if you want to see the code Peanut shell generates, we have a live or a web code editor you can use, and it's at the peanut.sh website. Thank you.
We have plenty of time for questions.
So with pipes, shells are very good at parallelism. Can you benefit from that at all?
Not really. Like there's not any like C construct that directly matches that. So we only use redirection operators, but not pipes.
Okay, I was hoping maybe you could turn out to be faster than C if you could pipe things and get them to parallelize in a good way, but maybe
The
not.
compiler is really, so it's a one-pass compiler. We try to consume as less memory as possible. So we really want to avoid doing things in parallel, but it could be interesting to see if there are like ways to program or use these shell features in a higher level way using C.
Hi. I was curious. I mean, it's a very interesting tool. I was curious what subset of C can be supported, or rather, the other way around, what subset of C cannot be supported.
So if we come back here, for example, PostgreShell doesn't have gotos. So if we wanted to support that, we would have to use some kind of trampoline mechanism, and then the shell code would no longer be human readable. Like we would no longer have the same structure on both sides. There's no floating point numbers in PostgreShell, so we would have to implement that from scratch, and it's not obvious how we would do that. Yeah, those are two examples.
I mean, I was curious, how do you handle structs, or like say unions, right?
Yeah, unions are kind of like structures. We don't support them at the moment, but like here in this example, like we have dynamic memory allocation because we have a heap, so you can reserve a space in that heap to have like two-layer structure. And so that's how we, like a structure is just like an array where you index with like names at specific locations, and so that's how we implement it. Sorry, what?
Do you have a tool that says, hey, this is a program that cannot be handled?
Well, Peanut will tell you. Like at some point it will encounter a construct that it's not able to parse or compile, and then it will just crash. Hopefully with a nice error message.
Any more questions?
So I wonder if you have considered ways to either automate or partially automate or assist in this auditing process.
The what?
To assist in the auditing process.
Like there's always the issue of using tools, because then you have to trust these tools. So we haven't really explored that. Like one way could just be to reduce the amount of code that has to be audited as much as possible. Still, like it's only about, so if we look at the size of the Peanut exe C source code, it's only 5,000 lines of code. 5,000 lines of code. And so like it could be done in a few hours maybe.
Perhaps you can have a decompilation process. You can compile, decompile, and compare.
We do have an option in Peanut where we generate the original C source code as a comment, and then we show the resulting shell code. So that helps with the comparison process. But then because we use GCC, and GCC could somehow change that original C source code, it could be misleading to use that for auditing. So really, we're on our own in terms of auditing, just because like we have to be almost paranoid of every tool we use.
Did any other questions pop up? In that case, let's thank our speaker. So that marks the end of our session, and we'll have a coffee break and continue at 4 p.m.
Hello? Yunjung, can you hear us? Yunjung? I should be...
Hello. Hi, can you hear me?
No, we should be hearing you.
I can hear you, but we're sorting it out in the room.
Okay, got it.
Can you hear it if I talk into this mic? Do you hear this microphone? Can you grab somebody from the room, please? The other room. Because she's... I did. When I joined it, like on my phone. Hi, can you hear when I speak into this microphone? By the way, she can hear the Discord audio also.
You could switch orders of talks if that yeah, if you want to like organize some technical things.
Yeah, so let's go to in-person talk.
Do that first.
No. Someone needs to go up. One of needs to go talk to the remote presenter.
You're not in the room anymore, right? Your phone. I just left the Discord. That's good.
So Anthony's happy to go at 4 or
That would be
now,
great,
so,
yeah. Okay. Try to connect the laptop.
Hello. Hello. Discord. No, it's. Hello. 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 Hello.
All right, now we're ready, almost. Computers are terrible things and they never work right. So, so we're switching the order while we get some technical things sorted out with the remote talk. So our first actual talk will be Tony Wasserman. A little bit about the design of software representation. I do want to say this is the SLE session, right? So the software language engineering body of knowledge. We've tried to have talks in this on this topic for a few years, so I'm really happy that we now have 3 excellent papers that fit into this category. So this is a new thing. So with that, so.
All right. No? Okay. Yeah? All right. So, hi, everybody. This talk I gave 2 weeks ago in Milan as a dry run, right, to see that it would fit in the time and everything. And what I discovered is that most of the people in my audience were quite young, and they were unfamiliar with any language that was kind of older than Java or Python. So we ended up stopping and explaining things, and so it ran a long time. So I'll try to go a little more smoothly through it, and if there are questions, we can handle them at the end. So what we're going to try to talk about are the ways that we represent software, and what we really try to do is step up from machine language and assembly language and all that ugly stuff that we used when I was a kid, and represent software in ways that are more meaningful to the human and to enable humans to communicate that information to others, whether that's in something that's non-executable like a use case diagram, or something that can be directly transformed into an executable program like a state transition diagram. We'll kind of cover the spectrum, but we're going to focus on the idea that you have to design your languages in a certain way, whether they're text-based or graphically based, and that there are some guidelines for communicating them from one person to another. All right. So if we go back, we can go back to Ada Lovelace, if you suppose, but really, I think if we go back into the 1940s with the very earliest computers that were being used, of course, by both sides during the Second World War to figure out how to launch rockets and do those kinds of things. But the things that go back to that time are flowcharts and transition diagrams and, of course, assembly code. Assembly code was a big step up from standing at the machine and flipping switches. If you've ever been to the Computer History Museum, you can go there and flip switches, which is, not a happy way to spend your day if you're trying to get any work done. But we moved in the 1950s to higher level languages. They, at the time, were called third-generation languages, right? Machine language, assembly language. And then Fortran and Algol and COBOL. And there was a big debate at the time about those languages because they didn't compile very efficiently. And machines were slow, memory was limited, and so there was a tremendous amount of work that went into writing the compiler as much as for the language design itself. And they weren't quite as fast, but they saved human time. So Jean Sammet wrote a book in the 1960s. She was president of ACM at one point and worked for IBM. And she put this Tower of Babel diagram there, which includes kind of all the languages that had been heard of at the time she produced the book. And the tower actually includes English, because there's been this long-standing dream that you can talk to the computer and say, this is what I want. And Warren Titleman in the 1960s wrote some software called Do What I Mean, and the idea that you could tell it what you want. And we're coming back to that now with the rise in artificial intelligence, the idea that you can say what you want to happen, and things like Copilot pop up and do their best. And of course, they're not quite there yet, but they're definitely an indication of where we are going or where we might be. So why are there so many languages when you look at that diagram? Well, first of all, in the early days, people designed languages like Fortran and Algol for numerical mathematical computation, and they were binary. And people designed COBOL, right, starting in 1958 or so, for business, and used decimal machines, right? So you had two families of machines that IBM built, and at the time they had about 70% of the computing market. So basically everybody in large companies ran an IBM system. People wrote extensions to languages for real-time systems. People wrote simulation programs. They wrote games. So, when you look at the languages used for games today, there are things like Lua, which, I never learned. But if I were working for a games company, then I certainly would. There also were evolving programming techniques. So we started with algorithmic languages, and then there was a whole school around functional languages, of which Lisp is probably the best known. And then we went to object orientation with Stimula and Clue. Most popular and widely used languages, you have Java and C++ and Rust, all of which follow an object-oriented programming style. And of course, people had to deal with things like concurrency and networking, and most languages evolved sets of libraries to deal with those kinds of things rather than designing a new language. But, down in the lower right-hand corner, it says vanity. People like the idea that they designed a programming language. So in 1958, when the first version of ALGOL was invented, there was a guy named Jules Schwartz who worked for TRW down here in Southern California, and he didn't quite like ALGOL 58. So he created his own version, and it's known as Jovial. Jovial is Jules' own version of the International Algebraic Language. So, you know, people really like the idea of, you know, designing languages that model the way they think for the problems they want to work on. And there's some excellent examples of it. Pascal is really as good an example as any because it was intended for education and fit into the mind of Niklas Wirth. So, but certainly a fairly large number of these languages that have emerged, they're like, you know, top 40 music, right? This is the popular one, and it was written by this person. And indeed, you can go look on the web and you'll see that every month there's a top 15 or top 20. What are the 15 most used programming languages last month? You know, it's like your own hit parade. That certainly is a factor. So if we look at things, there are a lot of different kinds of programming languages. And we won't go through all of these, but I listed a couple of examples in each category. So object-oriented languages, and research languages, teaching languages, systems programming languages. So those of you who may remember the lengthy design process that came up with Ada. Anybody remember that? Yeah, that was like 40 years ago now, right? You know, they came up with 4 candidate languages, and the Ada as a winner came, you know, really evolved from Jean Ishbia's Langage d'implémentation des systèmes, LIS, and then, of course, there's this whole pile of interpreted languages, of which Python is clearly the leader these days. And we have languages that are used on the web. Maybe you don't think of those as programming languages. They're rather markup languages or display languages, but HTML and JavaScript, PHP. Data management, I designed a language that was basically an extension of Pascal to handle relations as a data type. So I put my name in there on that, you know, on one. SQL, of course, is used to this day. It was designed in the 1970s at IBM San Jose, and lots more. I mean, we could go on indefinitely because we have our own Tower of Babel of languages today, which is considerably larger than Gene Samet's from the 1960s. There also are some notable failures, and you know, there's a lot of intellectual or financial investment in some of these languages. When ALGOL 68 was designed, Professor van Wijngaarden from Amsterdam sort of took everything that he wanted to put in a programming language and proposed that it be called ALGOL 68. Well, of course, nobody ever wrote a compiler for it. So nobody ever really wrote a running program in ALGOL 68. IBM, when they introduced the 360, right, the idea was to do away with these 2 families of machines, one for business and one for mathematical programming. So the whole 360 family was intended to support all kinds of programming from small computers to large. And as part of that effort, they designed a language called PL1. Nobody here has written a program in PL1. You have. I'm impressed. Okay. That's a separate talk. So great. So PL1 was implemented at IBM, and it took 7 years for them to get a compiler that more or less worked. So that was kind of a big undertaking. And of course, at the time, they were still building OS 360. Many of you know about this indirectly from having read Fred Brooks's book, The Mythical Man Month, right, where he described all the various issues that he encountered in trying to get those products out the door. All right. So now the other thing that came up along the way, all these languages that we've talked about were really aimed at professional software developers, people who studied programming or had a computer science degree, although it was really somewhere into the 70s before you could get, at most places, a degree in computer science. But the idea, again, of people, non-programmers, end-user programming, being able to do their own thing was an important step along the way. And what came out most visibly are what's called fourth-generation languages, right? So as we move up another level, and there were a lot of them. Okay, now some of them had a big following and they had good commercial support. Nomad is a very good example of that, and Power Builder. I've used for many years a tool called FileMaker, which has its own little scripting language. It was put out originally by Apple and is now still supported by what was a subsidiary of Apple. So Focus, Progress, a number of these languages, and they all had kind of the same mind behind it, which is conversational access to relationally stored data. And then it was just a matter of taste or which salesman got to you first. But all these languages in that category had the same flavor. And we see in those languages really the genesis of what we call low-code and no-code development today, of which there are, again, a very large number. If you were to go out and search on low-code, no-code tools, you'd get to 150 and going. It's a big number. And of course, it's dominated by a very small number of products like Mendix, a Dutch company, and by the tools that Salesforce has built, originally Force.com, and then subsequently they came up with 2 different languages at different levels of abstraction. And again, people are writing programs in these languages to deal with Salesforce applications. So if you're writing your customer relationship management system or your sales management system and you want to extend it and generate certain kinds of reports, then those languages are really well suited to that. And there's a big volume of those languages, and many of them are offered commercially for sale. Oh, you're running Salesforce and you're paying some number of dollars a month. For a few dollars more, as the title of the movie was, you can have these additional add-ons, and they're sold by independents. We also have WYSIWYG tools, what you see is what you get, that are used for building web applications. The best known of these are Wix and Squarespace, but what goes on more commonly are content management tools. Again, you're not writing in a procedural programming language, though there's a procedural programming language sitting underneath it. So I can design a website with Drupal, and if I need to tweak it, fine. There are hundreds, maybe thousands of modules that are add-ons that work in the Drupal framework. There are themes that allow you to customize things. And if you want to go beyond that, there's PHP. So you can go in there and script it. More popular than Drupal, of course, is WordPress. And WordPress, somebody told me, and I haven't checked it, but something like 40% of the world's websites run on WordPress. That seems like a big number, but I don't have the data to tell you otherwise. In any event, if you want to build a website quickly, you can be up and running with either Drupal or WordPress in 20 minutes. That doesn't take much programming skill. It takes some design talent and those kinds of things. So what this boils down to is that there are a whole lot of ways that people can go about expressing what they want to see in an application or in a website. Right? And these range from low-level machine processing things to highest level non-procedural languages and and other kinds of notations that show you what you want. There are all, I can't quit this slide without mentioning spreadsheets. But, you know, you can write macros for Excel, and people make huge bugs in them, you know, because the people who are writing the spreadsheets are the accountants and the finance people, and they're not usually programmers or trained in programming. And so, you know, when your bill is off by 2 orders of magnitude, it's probably because someone made a mistake in an Excel macro. All right, well, there are also a whole bunch of graphical languages. I mentioned early on things like transition diagrams, but in the 1970s, we saw a number of these things emerge. Larry Constantine and Wayne Stevens and Glenn Myers created structure charts. That was published in IBM Systems Journal in 1974, and it's a way of representing the architecture of a system and the information that flows back and forth between the various components of the system. It's not at all dynamic. Right? It doesn't support distributed systems or networking because it was 1974. But it was an example that if I wanted to show somebody how I wanted to architect my system in that era, the structure chart was great, okay, because I could see what information was being passed back and forth. I could separate global data from local data, all those kinds of things, right? And I could see the modular structure of my system. So it was very powerful. I could take each one of those modules and decompose it, right? Because I have subdiagrams, or I could attach code to each of those modules. So what we did, I started a company called Interactive Development Environments, and we were one of the first 100 .coms. And we built this product called Software Through Pictures. And this actually is an IDE shirt. And it's pretty old, but it's still there. Sort of no holes in it. But what you can see on the slide is that we're able to represent the various modules and the information being passed back and forth. And you can have things that are notation, that they're modified by the module or that they're passed back and forth. But what's interesting in the middle is this little box that pops up called module decomposition. And if you click on that, you get another window, and you can either use a program design language that is a high-level description of what you want that module to do, or you can write code. Okay? And if you write code, you can export it. So we actually were able to use the structure chart model as a way to generate the skeletons of programs, and if somebody wanted to go further, they could go in there and fill in the code for the module itself. Okay. TimeNet was a PetriNet tool, so people used PetriNets because they had concurrency features, and so here's a tool, and what you might be able to see is that these tools were built to run on engineering workstations. So we were very good buddies with the people at Sun Microsystems because every time people bought Software Through Pictures, they bought a Sun workstation to run it on. So they liked us a lot. But TimeNet, they built a custom user interface. I'm not sure what that ran on. David Harrell at the Technion in Israel created a notation called state charts, and then started a company where they built a tool to support state charts in that company. And that product was called StateMate. And this is a very high-level diagram showing the different kinds of diagrams that you could put in creating a state chart. For those of you who use Eclipse, you know, after they worked on the programming environment, they set up a group that built a modeling framework. So you can actually use that modeling framework to build various kinds of modeling tools. And I just showed you one simple example. Another one that I didn't show you, but I could, there are a variety of entity relationship diagram tools. So entity relationship diagrams for database modeling were created by Peter Chen in the 1970s, in the first issue of ACM Transactions on Database Systems. And entity relationship diagrams are very widely used. And our tool, as well as many others commercially, had graphical representations, and they could generate schemas for your favorite database management system from the graphical model. So, when you go to design a programming language, what is it that you do? What are the issues that you face? Well, a lot of people have given some guidelines for how to design programming languages, whether it's to support a particular application domain or a particular methodology, or your own personal preference. You know, do you like to start everything on a new line? Do you force indents? How do you feel about semicolons? All these things factor into the way that people design languages. Time isn't going to permit us to go through all of these things in detail, but it's all in the paper. But you need certain kinds of foundational structures to deal with different kinds of domains. So if you're doing string handling, Fortran wasn't so good for that. People built specific languages that were aimed at string handling, going way, way back to things like Snowball. But people also designed languages to support their own cognitive processes. And then they piled on a lot of libraries. If a language became popular, people wrote modules and themes and application programming interfaces and all kinds of other stuff to support that language and make it more useful. The best example of that these days is Python, right, which has a huge number of libraries aimed at machine learning and AI. So Tony Hoare wrote, "The objective criteria for good language design may be summarized in 5 catchphrases: simplicity, security, fast translation, efficient object code, and readability." Interestingly, 2 of those had to do with the internals, not about the language itself. Klaus Wirth, who's known for Modula and for Pascal and a few others, gave a very brisk description. You have to have a clear idea of how a language is going to be used, right? Because you need to select the right primitives for it. That's how you come up with your basic abstractions. And he made the point that you got to leave stuff out. If you put everything in, you end up with PL1, okay, or Ada, and it's too big to implement and too big to use. And he made a big point about that. Tim Peters, who's a guru on Python, gave a list of things in the Zen of Python. And what's interesting is that even though it's a different kind of language, there's an overlap. Okay. And then I took my own shot at it some time ago. I put together a book called Tutorial on Programming Language Design, and in that I listed these 5 things. For me, abstraction and modularity come first, because they're the way that you separate the issues and deal with them. So language design goes on, right? It's an ongoing activity as we sit around. Maybe some of you are designing your own languages as we speak. Others may be planning to do so or have recently done so. And now these new domains are leading to new languages. So, are the tools that are being used to support AI, is the AI going to design its own language? Or are there going to be notations that support AI? And of course, quantum computing has a different computing model, and because things can happen like Schrodinger's cat, how do you express that kind of notation? And I'm quite sure that will lead to new language advances. So that's it. That's my hometown, and an unusual, rare, sunny summer's day. So this finds me, among other addresses, and I'll stop there and take any questions you may have.
And yes, we have a little time for a few questions. So, Peter.
Thank you for the walk down memory lane. I'm probably one of the few people here that is old enough to remember some of those things that you were talking about. In particular, you mentioned that Algol 68 was never implemented. I think you should take a look at the Algol 68 homepage that refers to several ports of previous compilers that have been resurrected. Another point that a bit more serious is you characterized Ada as a failure. There's been a 2023 standardization of a new version of Ada, which is more than 40 years after it was first developed. And I think a language, even though perhaps the original aspiration of Ada of being the language that, in particular, the Department of Defense was going to use for all its software was perhaps overambitious. But to call it a failure, a language that survived for 40 years and with Ada Spark is also a topic of current use.
Well, yeah, I mean, I don't know how many people use it, but in fact, I was on one of the committees that evaluated the candidate languages, and I was on the national, it's an American standard that evaluated that DoD directive and recommended canceling it because so many exceptions were requested to writing in Ada. There were only 2 commercial implementations of Ada made available, and when you consider the tremendous amount of money that was spent on it over many, many years, I would call it a failure. Is COBOL 2023 or Fortran 2023? Those are both out now also. How many people are using the new version of COBOL, I wonder? So,
but with Ada, for instance, I'm familiar with the DDC Ada compiler that was developed in Denmark. I was actually a consultant on the project, which was a commercial success and used in the military in the Netherlands, and was actually the second compiler that passed the validation suite based on formal semantics development. Some of these things that you're saying, I can't really relate to.
Okay, well, let me put it a different way. How many people have written a program in Ada? More than I thought. Good, thank you. Thanks for your questions, Peter.
Hello, thank you for the presentation. It was a nice, it was very interesting. Since you are proposing a historical perspective, I think that I will ask the obvious question. That's what about the future? What do you think about the next steps if you like to play the futurologist? In which language will you bet, or something like that?
Yeah, so that's a dangerous question, one of the things that we know is that most people like their first programming language, and because it's the way that they were trained to think about programming. So whether it's Python or JavaScript or Fortran or something, which is why we have a 2023 version of Fortran and a 2023 version of COBOL and so on. So what's coming in the future? I hinted at that, and I think we're going to have new languages to support AI applications, and we're going to have new applications to support quantum computing, and maybe we're going to get something that deals with crypto in an unusual way, or encryption or security. Rust has some of those elements, and maybe it'll get extended in a way that will be popular. But I think that it's very hard at this point, not impossible, very hard for a new language to gain critical mass. And so much is open source as well. You can have a niche language, and we have a lot of those. But to have something that, when I ask the question, then everybody raises their hand, that's going to be hard to do, I think, because we've become more decentralized. Does that help? All right, what's your thought? All right. All right, good, thank you.
All right, well, let's thank Tony one more time, and then we'll move to our next talk. All right, our next talk is the remote talk on DSLs and Racket, so hopefully we can get that fired up, and they'll be there, and we'll still do question and answer afterwards.
Hello. Hi.
All right, let's go ahead, and you feel free to get started.
Oh, okay. So, okay, you can hear me, right? Okay. Hi. Hi, my name is Hyun Jung. Sorry, I'm hearing myself. There is an echo. Yeah, I will just start in the interest of time. I'll be presenting to you today my recent work on DSLs in Racket. Specifically, I will talk about language design objectives called design intents that language designers have, as well as how you can achieve these intents within the Racket ecosystem. And I will talk about how DSL authors exercise these intents and mechanisms for popular Racket embedded DSLs. Before I get to these points, let me first illustrate what you can achieve with the DSL in Racket with a simple game engine language. Let's suppose that you want to develop a language for creating a Clickomania game. A Clickomania is a one-player logical game where the where it's initially populated with blocks of different images or colors, and upon each mouse click, all the adjacent blocks of the same image get removed. To implement this game, you need to write code for various logical and graphical aspects. Logical aspects such as choosing random images, removing blocks if they're adjacent and are of the same image, and populating new images in the empty blocks, and so on. Graphical aspects such as resizing images with respect to frame size or block size, and setting the background image as well as block images, and so on. Which means that if you were to write this in vanilla Racket, you would want to implement a data structure to represent a game state and a global variable in the form of mutable matrices to keep track of states of blocks, a function that eliminates all the adjacent blocks of the same image or color, a function for adjusting the size of an image based on a specified target size, and many more. But all of these code repeat in any Clicomania game, which means that they can be abstracted away in a DSL with a few lines of code. Okay, this aspect of abstraction is quite well known about a DSL. What else can we do with DSLs in Racket? Aside from specifying domain-specific functions, say if you, a language designer, want to use curly braces for a grouping of statements, as in C or Java, you can add this new syntax to your language. Or you can require all the DSL users to specify certain bindings in any program written in the DSL, and make the program crash if they fail to do so. Or you can ensure that your DSL programs can work with the host language programs through imports and exports. Also, you can allow the user of your language to write macros to extend the language itself. All of these are possible within the Racket framework. So now that we have briefly seen what it's like to use a DSL embedded in Racket, let's move on to the first contribution of our paper, a taxonomy of so-called language design intents. Language design intents refer to implicit objectives or goals that a language designer has in mind with respect to how their language look and feel or behave. I will describe each of the intents with the following 3 DSLs. A configuration language called frogconfig, a type language called typeracket, and a shell-like language meant to work with this host language Racket called Rash. So first, custom syntax. While it is true that you can keep the host language syntax as in the frogconfig DSL, you can also add a new syntax for representing different information, such as type information for typeracket. Even more, you can have a whole new syntax, as in the shell language part of Rash, or a combination of shell syntax and Racket syntax. Moving on, the second intent is called custom semantics. This refers to DSL-specific meanings assigned to language constructs. Let's take a look at frogconfig DSL. This DSL provides bindings that are used for generating a configuration file. And likewise, Rash provides shell-like bindings as it tries to replicate behaviors of a shell language. Although we expect each DSL to have domain-specific bindings, as the name suggests, there are some nuances to be found here. For example, in typeracket, while it has typeracket-specific bindings, such as define type or other bindings here that are used for specifying types, it may override host language bindings, such as define here, to provide new semantics to the existing bindings of the host language. Now, shifting away from syntax and semantics, an interesting intent you can achieve is to control import and export related behaviors. An interesting DSL example to look at is frogconfig. This DSL requires all the program written in frogconfig DSL to export these 3 bindings: init, enhance body, and clean. Omitting any of these bindings will cause the program to crash. And in typeracket, while it looks like typeracket code is importing other typeracket code, as in the Racket code importing other Racket code, the underlying behavior of import and export differs as it incorporates all the type information. However, Rash is an example of language without import and export control, as it is designed to allow its users to import or export other Rash code without constraints or additional information. Next intent is called macro support. That is supporting the users to write and work with macros. As for Rash, because Rash is meant to be a shell language where the users can write normal Racket code, it intends its users to be able to enjoy Racket's macro system. Type Racket also allows its users to write Racket-like macros. Frog config, on the other hand, is intended for writing configuration files, so it is not meant to provide macro support. Moreover, a DSL can be designed to let its users read and write host language code as in the host language, and we call this intent syntactic embeddability. In frog config, Racket code can be read or written as in Racket and successfully compiles most of the time, meaning Racket code that exists in the frog config program is effectively embedded. Another language with this intent is Rash, as the language allows its users to switch between Racket and Bash language. On the other hand, when you look at type Racket code, you cannot read Racket code as if it's in Racket. Instead, it requires users to annotate type information. Hence, this is an example of DSLs syntactically embeddable under certain constraints. Next, DSL authors can develop a DSL to make it work with the host language, which is called interoperability. In other words, if running the DSL code results in values that can work with Racket code, then we call that the DSL is interoperable with Racket. Interoperability is almost always a feature and a goal in Racket-embedded DSLs, as in the case of these three languages. And lastly, another useful design intent is to equip a language with an ability to statically check certain properties, hence called static checking. For example, a type Racket is an example with this intent, as a common form of static checking is a type system, and this is a language where a type system is added to the language. On the other hand, both Rash and frog config are DSLs that do not statically type check or perform other static checking. Now that we have seen all the 7 design intents, let's look at the mechanisms that enable them in Racket. The enabling mechanisms can be categorized into reader customization and expander customization. The first category refers to customizing a reader. A reader is a Racket-specific parser that converts the source code into the Racket notation based on S expressions. In Racket, you can access and rewrite the reader of your language and do several things. You can reuse a parsing function called resyntax from the Racket itself, or you can add a new way to parse to handle parsing by adding this information to a parameter of the function called readTable, and use this as a new way to parse your DSL code. So once this is put together as a customized reader, now it can handle new syntax added to your DSL, such as curly braces or a block of statements, as we've seen earlier. Further, you can redefine a custom parsing function and provide it through the reader. And this will enable a custom syntax such as non-S expression syntax that looks more like a Python code here. Additionally, you can implement a reader that enables multiple syntaxes, such as my hybrid resyntax here, which allows both S expression-based syntax and non-S expression-based syntax. So, based on the extent to which this parsing function as well as its parameter are adjusted, we came up with a classification of reader: default, extended, custom, and hybrid. And when put together and linked back to the language design intents, this is what enables custom syntax of a DSL. Another set of enabling mechanisms has to do with expander customization. And for this, we have come up with 5 major ways to customize the expander environment. Default bindings, custom bindings, default bindings at phase 1, custom module begin, and other custom implicit forms. I'll briefly describe them with examples. DSL semantics are refined through bindings provided in the expander environment. An expander environment consists of initial set of bindings which the Racket expander uses to recursively expand to a fully expanded program which can be understood by the compiler. As briefly listed earlier, you can choose to provide all the default bindings from Racket. You can provide DSL-specific custom bindings through this environment. You can provide Racket's default bindings at phase 1, where phase system is used to separate runtime bindings from the compile time bindings, but with more fine-grained details. Or you can provide redefined special bindings known as implicit forms used to facilitate subtle customization of semantics, including the ones such as module begin for declaration of module here, or other forms used for function application, and several more. So when all the customization options are put together and linked to the language design intents, what we have found is that custom bindings and customizing other implicit forms enable custom semantics. Customization of import and export related bindings or customization of implicit form used for module declaration enable import and export control. Default bindings provided at upper phase 1, enable macro support. A combination of default reader and default bindings enable syntactic embeddability. And a combination of default bindings, custom module begin, and other custom implicit forms enable interoperability. And lastly, custom bindings and customization of implicit forms are the mechanisms that enable static checking. Further, we analyzed how popular Racket-embedded DSLs achieve these intents by customizing their readers and expander environment. We chose the 30 existing DSLs based on their popularity measured by their GitHub stars. So in the interest of time, let me focus on a few things that stood out. First, before this study, it was commonly believed that language designers are more likely to extend the Racket syntax rather than having its own custom syntax. This turns out to be true, but the difference was surprisingly not so large. Besides, a majority of the DSLs were using the default Racket syntax. Second, we hypothesized that changing these special bindings, known as implicit forms, would be uncommon due to complexity involved. However, when we looked at it, around 40%, 36.7% for custom module begin, and 43% for other custom implicit forms. So around 40% of the DSLs studied reinterpreted the implicit forms, changing some default behavior of the respective language. And lastly, as the DSL authors are likely to have written macros when designing their languages, we assumed that they would appreciate the extensibility of Racket. Hence, we expected a majority of DSLs are likely to support its users to write macros. It turns out that 2/3 of the DSL studied provide macro support, confirming this hypothesis. However, 1/3 does not, suggesting that DSLs may intend to prevent its users from extending the language. So for more on the findings, please check out our paper. To conclude, in this work, we have proposed a taxonomy of language design intents, as well as their enabling mechanisms in Racket's ecosystem. And in particular, we analyze existing Racket-embedded DSLs to make observations about how Racket's metaprogramming facilities are used to achieve the design intents. That's the end of my talk, and thank you for listening.
Am I on? All right. Any questions?
Hello?
Can you hear me?
Yeah, I can hear you now.
All right, thank you. Okay. So I guess one question I had was, what sort of hypotheses, were there any additional hypotheses that you didn't get a chance to present here, especially ones that maybe the results were different than what you expected?
So yeah, these were the three main, so we made 3 different hypotheses per, in our work, we presented 3 different hypotheses per reader customization, expander customization, and the design intents. And these are the ones that we found more interesting than the other ones. So I think the other ones that they were, so we got them from the Racket guide and the beautiful Racket book, the assumptions about the way people design languages, and they were mostly sort of confirming our hypothesis, but the ones that I presented here were the ones that I thought was interesting to discuss.
All right, thank you. Any other questions from the audience? All right.
I wonder whether you have perhaps used other sources than the source code of the DSL implementations to substantiate the observations that you have. Like in particular, did you encounter any discussions on the design decisions that you've learned something from?
Right. So we have looked at the source code, and we have also looked at the documentation and the description of the language. Some of the source code comes with some, some README documents or other additional documents that describe what they intend their language to be used as. So we were using them as the sources in addition to the implementation code itself.
Were there perhaps cases where if the language implementers had more knowledge about how to use macros, for example, or how to customize their syntax, perhaps they would have used other facilities of Racket?
You mean that they could have done things better or differently, but they were not doing that? In that kind of?
Yes, exactly. Perhaps because there was a knowledge gap on the facilities that Racket provides.
Yeah. So I suspect part of the reason why we see a majority of the languages use the default syntax as is perhaps has to do with the lack of awareness among the DSL authors about how they can customize their syntax. So I think, but that is just the assumption, and we didn't get to really talk to all the DSL authors. So yeah, and everyone's skill sets differs, so it's difficult to tell whether they were doing it because they were not aware of some of the meta programming facilities.
Thank you very much for your talk. I think in the interest of time, we'll move on to our third talk for the session. So let's thank our speaker one more time. All right. So our third and final talk for the SLE session will be given by Robert Stunek. All right, and so this is the linguistic theory behind Blockly languages. So, Robin, please.
So, hello. In this talk, we first show you what Blockly languages are and what Blockly is. Then we look at some linguistic foundations, especially at some grammar formalisms for the definition of such block languages, and show how the mapping between the grammars and the block languages work. And at the end, we introduce some syntactic sugar and enhancements to some of these grammar formalisms to simplify the notation and also generate more complex blocks. So first of all, what is Blockly? Blockly is a library from Google to create such block editors like the one on the left, right-hand side here. And in a block editor, you don't edit the text in a free form like in a text editor, but instead you have each syntax element available as such a block here. And then you program by connecting these blocks together just like in a jigsaw puzzle. And by this, you are actually directly editing the abstract syntax tree of your program. And block editors like this are mostly used in learning platforms like Scratch or Code.org. And one reason for this is that you can't make these classic syntax errors, like, for example, to forget the semicolon at the end of the line, or by completely forgetting this B letter here. Because if we would do this, then the user would directly see that there is a big hole in the program and sees that he has forgotten something. And if we compare this to a text editor, then you really would have to read the whole text to see where something is missing. And then you don't even know if the user tried to increment A or if the B letter is missing here. And if the user then now wants to fill this block input, he can refer to the toolbox where each syntax element is available as such a block, and he can then drag some of these blocks and try to connect them. And what's really nice now is that only these blocks will fit into the input that are allowed by the language. So for example, this return block or this comma separator won't fit into our block input, but this identifier block here will. And Blockly now really abstracts over this concept and allows us the creation of such toolboxes for arbitrary languages. For example, for general purpose programming languages like JavaScript, where we have function blocks or return block, and also for minimal languages like an expression language where we just have addition or multiplication blocks, or also some domain-specific languages like state machines where we could model our transitions on the start and the end state. So the question now is, if I have a custom domain-specific language, how can I tell Blockly which kind of blocks I want to have? Let's assume, for example, such an assignment block here and an identifier block. And for this, we have two options. We can directly define these blocks in JavaScript code or define them in a JSON object. And if we look at the JSON definition of this assignment block here, we see we first give this block a name, and then we define the message of the block, which is its visible part, which mainly consists of the equal sign here at the end, but also has placeholders for our two block inputs. And these placeholders are then defined in this arguments array, where we first specify which kind of placeholder this is. So input value stands here for block input, but we also have, for example, placeholders that could stand for this text input field here on this identifier block, or some drop-down fields and so on. Then we give our input a name. And the most important part here now is this check array, which is an array of node types that are allowed by this block input. And what Blockly then does is to compare this array with the output array of another block and check if they intersect or not. And if they intersect, so if they have a common node type, then they may be connected and otherwise not. But what you see here in general is that you really have to write a lot to define this simple assignment block with only an equal sign on it and two block inputs. So you can imagine if we have a whole language, then you probably have multiple hundred lines of code, and you can't just look at your definition and see at a glance what your language does. So what we want to do instead is to use the natural representation of the language, which is its grammar. And this has been done before for context-free phrase structure grammars. And if you now ask what are context-free phrase structure grammars, they are actually just the context-free grammars that you all know by Chomsky. But context-free grammar actually just says that this is a grammar that could create a context-free language. And of course, there are other grammar formalisms that could also generate context-free languages. For example, dependency grammars that we will see later in this talk. So we really have to call this grammar here by its full name, context-free phrase structure grammar, where phrase structure grammar is the term coined by Chomsky for his kind of definition with non-terminals and production rules of the regular context-free and context-sensitive grammars. So if we now look at the production rule here that could correspond to our assignment block, we see that this is much more compact. We have here the non-terminal on the left-hand side, that corresponds to our block output, and the other two non-terminals correspond to our block inputs, and then the terminal corresponds to the text on our block. So we see this is much simpler, and this mapping has been shown before by Verano Merino and von der Storm. But what they also have shown in their mapping is that there are some inconveniences. And the main problem is that a production rule is not required to have terminals in them. So we also may have production rules without any terminals at all, and these then don't correspond to useful blocks. So this is really apparent if we look at the linguistic foundation where phrase structure grammars come from. So if we look at the sentence, this is a phrase structure tree in a context-free phrase structure grammar, and the analysis here, we really see where this name phrase structure grammar comes from. Because the sentence here mainly consists of two phrases, the verb phrase and the noun phrase. And then the verb phrase again consists of a determiner and a verb. So we see we have in the upper part all these non-terminals that are connected to each other, and then only at the bottom we have the real words of our language. And if we now take the structure here and directly map this to a block editor, we see since all these non-terminals here are non-terminals, they don't correspond to a word of our language. So we have now all these empty blocks that look exactly the same, or at least quite similar. So if you now try to build this program and construct this, you have to connect all these empty blocks and you have to choose the right one, because otherwise they won't fit. So you probably agree that this is not that practical of a block editor, not really useful. And the reason for this is that what we see here is not a representation of our language as a block language, but instead we model here the meta language of our sentence. So what we really want to do is and have to do in the mapping is to delete all these terminal-free rules from our grammar, which then means that our structures don't correspond anymore, which we will see later. So we really want to just delete all this, and it does not really help if we would add the names of the non-terminals here to the blocks, because now at least we could differentiate between them. But now you can't even see which sentence you try to model here, because you really have to know, you have only to read the words at the end on the right-hand side and ignore all this clutter in front. So we really just want to remove this, but if we would do this, then the blocks of our language would not be connected anymore, because at the moment they are just connected by the non-terminals. So what you have to do now is to decide for each phrase which word of the phrase is actually the head. So for example, the head of the sentence is the verb phrase and the head of the verb phrase is the verb. So maybe you know head-driven phrase structure grammar, where you also have the concept that each phrase has a head. So this means now that this verb is should actually be the root node of our block editor. So if we now model this, we see again, if we read from top to down and from left to right, the sentence, this is a dependency tree. But now we don't have a phrase structure anymore, because what we do instead is to directly now model the dependencies between these words. And if you now compare these structures, you see they don't look any more similar. So phrase structure grammar is actually not that good of a formalism for the definition of block languages, because what you're trying to do in a phrase structure grammar is completely something different. You don't want to model phrases in your block language, but you want to model the dependencies between the words of your language. And that's actually exactly what a dependency grammar does. So if we now look at this syntax tree of a dependency grammar of the sentence, we see we don't have any non-terminals here, because what we do instead in a dependency grammar is to just model the dependencies between our words. And if we now compare these structures, we see they look exactly the same because they try to model exactly the same. So the question is now, why should we use phrase structure grammars for the definition of block languages if they model something completely different, while instead dependency grammars model exactly what we want to do? And if we now look a bit at the history, we see that dependency grammars are even a bit older than Chomsky's phrase structure grammars. The father of modern linguistic dependency grammar is Lucien Tenière, and especially his work Éléments de syntaxe structurale, which is a book about syntax that is completely based on this dependency grammar. And if we look at the publication here, it does not seem that Chomsky's work should be the younger one here, but the reason is for this is that Tenière's work was only published 5 years after his death, and he started his work more like in the 1930s when Chomsky was still a child. And the concept of dependencies between words is even older. It was already present in the earliest known and preserved grammar by Panini in the 4th or 5th century before Christ. And the term dependency was first used in the 12th century AD. So what we're trying to do here is not to introduce something new, but we just noticed that the structure in block editors actually correspond to this age-old formalism of dependency grammar of linguistic. And if we look at linguistic, we see that dependency grammar is a big alternative to phrase structure grammars by Chomsky, while in computer science, they are not really that well known and only used in natural language processing or computer translation. And some aspects of dependencies between words are nowadays visible in large language models, but in general, in computer science, dependency grammars are not used at all, which really is a pity because there's much theory behind them in linguistic. And the first who really gave a mathematically precise definition of these dependency grammar were a few years later Hayes, Gaveman, and Robinson. And what's nice is that they were not only the first to formalize dependency grammar, but to also show that their formalism is actually weakly equivalent to phrase structure, context-free phrase structure grammar by Chomsky. And what weakly here means is that if you have a dependency grammar, you always have a natural corresponding context-free phrase structure grammar where your syntax trees also look the same. But if you go the other way around, you don't have this natural correspondence because you have to make some adjustments and your syntax trees then don't correspond anymore. But still you could create the same set of languages, the context-free languages. But you see a similarity here in the mapping that you have to make these adjustments if you start with a context-free phrase structure grammar and go to a dependency grammar or to a useful block editor. So if we now look at this formalism by Hayes and Gaveman, we see this mainly consists of two concepts. The first concept is that we group words that behave syntactically exactly the same into some categories. So what this means is that all these words here could occur at the same positions in a syntax tree and also have the same kind of dependence. So in a syntactic way, they behave exactly the same, and we could then group them. And then we have multiple such categories, for example, an assignment category with an equal sign, or a name category that accepts an arbitrary identifier as a word. And the other concept of dependency grammars are dependency rules, which look quite unfamiliar at first, but which mainly could read like a term definition or a regular production rule. So that we have on the left-hand side here a head category, and in the body here we have some our dependent categories. So this assignment here has two dependents, a name and an expression, and each dependency rule has such a triangle. And this triangle marks the position of the word of the category, so in this case the equal sign, between its dependents. So the equal sign stands between the name and the expression. And in general, the format is that we have a head category on the left-hand side here, and then in the body we have first some arbitrary amount of left dependents, followed by the word of the head category, and then some right dependents. So for example, the declaration category has no left dependence, but is directly followed by a word of the assignment category with all its dependents. And then at the end, we have a semicolon. And if we now take such a dependency grammar and map this to a block editor, we make this just by taking each dependency rule and mapping this to a corresponding block. So for example, this assignment rule here corresponds to a block where we have a block input for a name. Then we have another block input for the expression, and in between we have the word of the category, which is the equal sign. And the same is true for the other rule. So we have a block input for an assignment block here, which means that this assignment block here will fit into the input. At the end, we have a block input for a semicolon. But the difference now is that this category has multiple words, so we don't map this to a static string like with this equal sign, but instead we give the user a choice which one of these words you want to use and map this to a drop-down field. So if we compare this now to the JSON definition of the blocks, we see that each dependency rule firstly corresponds to such a definition, and the body of the rule corresponds to the message string of this block, and the word of the category corresponds to the text on this block. And we use the head category as the name of the node type of the output array, and the other category names, the names of the dependents, we use for the node types in the arrays of the connection checking of this block input. So what we see is that dependency grammars really directly model what we want to do in a block editor, and that also this mapping is extremely direct. But what's really nice is that we could make this even better if we introduce some syntactic sugar to dependency grammars that is also present in, for example, in phrase structure grammars by Chomsky that we introduced there. And by this, we could then generate more complex blocks, like for example, blocks with multiple texts on them, or blocks with multiple items in these connection arrays, because at the moment, each array only has one single item in them. So the first thing that you notice is that most of the time, if you define a programming language here, then there is that all your categories only have a single word in them. So it does not really make sense to split this declaration here, and we allow to just inline the word directly into the rule, which then also look a bit more similar to a term definition or a production rule. And the next thing that you notice is that you sometimes have constructs like do, while, or ternary operator, or left and a right brace or bracket, so multiple words that actually are part of the same concept, which is visible that this right bracket here occurs only at one position as a dependent, which is here in the left bracket. So what we allow then is to just inline this rule directly into the parent, which again simplifies the notation of our dependency grammar, but now also gives us the option to generate blocks with multiple words on them, because we now have multiple strings here. And the last thing that we want to show is that you sometimes have constructs like you could print an addition, you can print an identifier, you can print and so on. So you really have the same rule multiple times, which is really tedious to write if you have that a lot. And the same problem we also have in production rules in context-free grammars. And what we there have done is to introduce this EBNF notation that you could print an addition or an identifier. And the same we could introduce now for dependency grammars. And what's nice about the syntax is that we now could take these multiple items here and map them to multiple items in the connection array of Blockly. So we see in Blockly, we actually have the same syntactic sugar. We could define multiple blocks with a single item in them, or combine these blocks to one block with multiple items. Yeah, and then there's more in the paper, which we won't show here. But what we have seen is that dependency grammars are describing exactly what we want to do in a block language, and that they are a strong contender for a meta theory of block languages, and probably also in other applications in computer science, especially in the field of software language engineering. Thank you.
Thank you. It was very excellent. So questions from the audience? Thomas.
Thank you very much for this interesting talk. I wonder to which extent you implemented this and then perhaps automated also a conversion from well, one type of grammar into the other and the other way around?
We have not implemented a mapping from context-free grammars to dependency grammars, but from dependency grammars to these block languages. So all these blocks that we see here are generated from dependency grammars. And I don't know, I think that there are not any automatic tools to map context-free phrase structure grammars to dependency grammars, but there are some mechanisms how to do this in the proofs, how, of Hayes and Gaveman, where they showed that the languages are equivalent.
Yes, exactly. And given that, of course, a lot of DSLs are defined, or languages are defined using grammars, I was thinking that this could be an interesting strategy to pursue. Did you consider this option?
I'm considering this because I'm considering if it's worth to formalize this proof, and by doing this then also to automating this. But what we are now actually at the moment are trying to do is, what we have done here is to just look at the syntax, and we are considering to implementing some semantic aspects. But you're right, since all grammars are actually defined in context-free phrase structure grammars, this would be good, but what we're suggesting here is more like for if you want to define a new language, that you then probably not should not start with a phrase structure grammar, but perhaps with a dependency grammar directly, because then you also could directly model how you want these dependencies to look like. Because if you start with a dependency grammar, then you have to decide which dependent is the head. So this is arbitrary, and you have multiple possible mappings then.
So is your advice then that language workbenches should implement?
Probably too, yeah.
Okay, thank you very much.
Maybe to follow up on that, it sounds like you would be proposing dependency grammars as a sort of an abstract syntax representation. Is that a fair thing to say?
Because you're by this directly have the abstract syntax and don't have to make this mapping then afterwards.
Yeah, okay. Because I guess when you started, you see the blocks in some of it. I initially see abstract syntax there.
Yeah.
I think, oh, it's abstract syntax with a few terminal symbols to give the nice names. But that's not it at all.
So yeah, this was the point that in Blockly you are actually directly editing the abstract syntax, and so dependency grammars describe this.
Yeah, exactly. Yeah. Very interesting. So, all right.
This is very nice, and I've never actually heard of dependency grammars before. So a big problem with the idea of structure editing in normal textual editors is just the fact that it amounts to a lot of tree manipulation of the AST. It seems to me that maybe a dependency grammar is a flatter tree and therefore is more easily manipulated structurally. Has anybody tried that?
I'm not aware of this, but I think so too.
Okay, thank you.
Any more questions?
All right, if not, we'll thank the speaker. Then I have one thing to say after we thank our speakers. All right, thanks again, Robin. As Ralph mentioned before, there is a plan for dinner tomorrow night, so we'll be leaving from 6 o'clock in the lobby of the hotel. If you've not yet signed up, you have just officially missed the deadline, but of course this is an artificial deadline. If you want to go, talk to me or sign up. Try and do that soon. If you had issues with the website or something, just come talk to me now and we'll make sure you get you on the list and we'll be ready to go. So, all right, thanks again, everyone.